Hello, Faizal. Faizal, are you there? Faizal, are you there?
Hello. Yeah.
But probably off your mic or the complex for now. Okay. Oh yeah.
Yeah, Assalamualaikum semua, and good morning to all the participants. Can you all hear me?
Okay.
Okay, very good. So waiting for, I think Dr. Hisham is already in the meeting, Google Meet. So we will wait until 10 a.m. Hopefully we can start the session sharply at 10 a.m. Okay, hello Dr. Hisham.
Hello, Assalamualaikum.
Salam. You are ready for the presentation, right?
I'm trying to upload my slide first. Yeah, I think I'm ready.
Okay, once ready, then we will just proceed. So because today is our second day of our conference, and for all the participant information, let's say you couldn't make it to the yesterday's sessions, you can find the recording of the sessions in our YouTube channel. So the whole sessions, the whole conference sessions, since from 10 a.m. to I think 4 p.m. is already in our channel. Just maybe for reference, because I was told that some of our participants requested for the recording to be available. So just to inform that the yesterday sessions and the today session will be available in our YouTube channel. Okay, it is now 10 a.m. I would like to greet a very good morning to all the participants who have the ability to join our conference today and can be present. I'm very thankful for your presence at this conference, and especially to today's sessions. Actually, we have two keynote speakers this morning. One is Dr. Hisham from UTP, and then after this, there will be another session that will be given or presented by Prof. Haris Ahmad, the chairman or the director of Photonics Research Centre. So a very good morning to all of you. First of all, I would like to introduce our first keynote speaker this morning, which is Associate Professor IR Dr. Hisham Muhammad. I think he is by nature is a civil engineer. He is a lecturer from the Civil and Environmental Engineering Department from University of Technology Petronas, Malaysia. So he obtained his MSc in Soil Mechanics and Environmental Geotechnics from Imperial College, London, and his PhD in Geotechnical Engineering from University of Cambridge in 2004 and 2008 respectively. Currently, he is an associate professor at the Civil and Environmental Engineering Department, UTP, and then some of his notable involvement of construction monitoring projects using innovative fiber optic sensors include monitoring tunnel deformations at London King's Cross and Singapore's Mass Rapid Transport, which is MRT Circle Line in 2013. He joined the Geotechnics Division, Ministry of Mobility and Public Works in Belgium for a year and was involved in monitoring ground excavation and construction project of the world's largest shipping lot in Antwerp. So without further ado, I would like to give this floor or sessions to Prof. Hisham. You may start, Prof. Hisham.
Thank you very much, Mr. Chairman. Let me upload my slide to the screen. Okay, are you able to see the screen? Mine?
Yes.
Okay, so just a talk on, good morning everyone. First of all, thank you so much, Mr. Faisal, for introducing myself. It's an honor for me to be with you all this morning to share some of the things that that have been working for the last 5-6 years on, and today's topic is basically on one of the applications of fiber optic sensing for slope monitoring. Basically, there's some work which I did for foundation works for underground tunnels. So, but today I'm just going to focus on the topic of slopes and retaining, earth retaining structures. Right, so the content will be obviously to show you the technology of distributed optical fiber strain sensing. Perhaps you've been listening quite a lot on other technology of fiber optics. So my area is more towards distributed sensing. And the application for this morning, I'm going to show you for landslide applications, some of the technique that we use to monitor the movement, point anchored system, inclinometer, retaining wall, and some other applications. And I will conclude later on. Right, so distributed sensing is basically using optical cables where you can deploy the sensor on slopes to monitor the ground movement. You can have two ways. One is to install on the ground surface, and the other one is where you can embed it in the ground. When you install on the surface, you can put it in the point system, such as shown in the photo there. So when there's some landslide, you can pull the cable and you can detect the stretch of the cable. Therefore, you know where is the location of the landslide. On the other hand, if there's some movement inside the ground, you can, and also you can install in the form of inclinometer, or also you can incorporate in the earth retaining system such as the soil nails. I'm not going to go through what is fiber optic sensing, but basically it requires the transmission of signals of lights through the fiber, and the fiber is very fragile. It has to be protected. When the fiber is very small, mainly using the that all the information coming through the core, which is very small. I like to talk normally to other people who doesn't understand what is fiber optics. Human hair is basically 50 micrometer, but the size of the core itself is just 8 microns. So it's very small, very fragile. It needs to be strengthened. So there are many package of cables that we use. So it's very important to use proper cables for civil engineering or for other field applications. So I'm not going to go through the advantages. We know these very advantages in terms of the insensitive to electromagnetic interference and quite durable as well. These are some of the cables which I used to use. Some are very simple, single fiber, some are ribbon fiber. Then you have standard telecom cables. The most important in monitoring is that you use to monitor. Basically we have two main parameters: strain measurements to measure the elongation of the fiber, but the cable has to be tight buffered. So the jacket has to be, which we stretch, it will transfer the physical stress or the strain into the core. And when you detect the changes in the strain, you can measure the strain. And the other one is the temperature cable, where the cable function is not to allow stresses to be transferred. So this is quite useful to do measurements of temperature. Of course, the prices ranges due to the complexity of the cables and the availability. Right, so these are the main three components or basic configuration of sensing. We have FVG. We used to say this fiber FVG is kind of like point sensing because you need one sensor with one cable. The one that I'm going to show you is basically distributed sensing, where the cable becomes the sensor. And we have also the quasi-distributed sensor, where you can have a series of FVG sensors connecting to each other to become a multiple sensor. And at the bottom there's some 3 photos just to share with you the difference between having point sensors. If you have 25 points to measure over a slopes surface, you will require 25 cables going into the logger, which means 25 channels, which is quite messy and difficult to handle. On the other hand, if you have a fully distributed system, you can configure, you can lay out the cables in many shapes to cover the area, and you just need one channel to do the measurement. So it's quite advantageous, and also can potentially replace thousands of sensors and become a low-cost system. So basically, most of you are those on the photonics, you probably know this. We are actually, for distributed system, we can have relay, we can have Brillion, and we have Raman scattering. So for measurements, for strain, we use Brillion scattering. Where the logger, I'm using just a commercial off-the-shelf sensors. I do not do any kind of photonics, and of course, I'm a civil engineer. We just apply the sensor and try to think of how to deploy in the field. It's just to show you how the measurements make. You have the optical pulse sensed into the cable, which sends back the scattering lights. And if the scattering lights changes in terms of frequency, you can detect that to resolve the strain. And because the light speed of light is constant, you can also detect the position where the scattering light occurs. By resolving the time, you can also know the position, and therefore you know the readings of both strain and location to obtain the distributed reading. The other thing is that the disadvantage of BOTDA is that it cannot take dynamic measurements because it requires a few minutes of measurements to complete the whole reading, because it depends on the very weak signal. It requires a lot of averaging time. And then, but the advantage is that you can get a lot of readings. You can have up to 100 data points per reading. So just to try to think of how you're going to use this for measuring on slopes, we can actually, as I mentioned earlier in the talk, you can put it on the surface as a ground wire extensometer, and also to measure the extent, the depth of the landslide through installing into a borehole. Okay, so we can integrate as an inclinometer and measure the movement below the ground surface. I'd like to start with this simple experiment conducted just to give you the idea how it looks like if we are measuring a movement of an earth embankment, and on one part of the embankment actually being there's a kind of like landslide. We can see that it can detect the movement. This is one work done by the Public Works Research Institute of Japan, where you have this model of a slope, and then there's one guy trying to pull a plate which is placed at the bottom of the embankment. They have also many gauges there to just to compare the readings. So as the guy actually pull on one side, you will shear the slope, the ground, and then it should detect the movement by the sensor. So this just want to show you the slope comprising of one part some gravel type of soil, and the other half is some soil type, and the soil fiber is actually placed inside, which they dug up to show you the how it looks like physically. And the reading looks like this. So as they pull more, you get more strain at that particular section there. So this is just to show you that it able to detect quite clearly on the movement of that side. So no movement at the far edge of the movement zone, but large strain at the deformation part there. So with that, there are many other researchers who would like to explore this application. One of that is a colleague from in Switzerland, Dr. Michael Iten. So he installed cables along the roads and also along the slope. This is actually to detect the boundary of landslide. So you can see there's small trench being dug up, and also cable with attachment of anchors. The reason why you put anchors there is to try to grip the soil, because if you just install bare fiber, there will be some kind of slippage, which is not good. You may miss the actual movement of the ground. And some researchers also use geotextile, as you can see on the right hand figure there. There's also research done to even incorporate fiber inside pavement, asphalt pavement, you can see there. Right, so I just want to show you this diagram here is an impression of it as a landslide occurring on the slope. If you install the cables from A to D, which is across horizontally there, so it gives you different reading than laying the cable in a downward pattern there. Okay, so let me try to find my highlighter. Where is it? Spare a second. Oh no, it's not it's not the one I want. How do I switch this? Okay. Laser pointer. Okay, so let's go back here. All right, so there's the downward laid fiber give you different reading than horizontally laid fiber. So when I mentioned just now, the boundary of the landslide is when it's actually on the edge here. That is where you have the high slope soil shearing, and you would expect to have high peak of strain at that boundary zone at point B and C. So this is the expected kind of reading that you can get from the distributed sensing. And the difference of having fiber laying inside the ground and also compared to the one that is anchored. So it gives you also different reading, as you can see here. So there are many other works done by researchers. As I mentioned, this is one of that work by the Cambridge group. I also helped this colleague of mine, Mr. Koson Janmota, a work by to install geogrid fiber optic inside a trench on quite a gentle slope near the motorway M25, which is a ring road in London. Try to detect the creeping movement of slopes. This is one work by my colleagues from the Geotechnical Division, and also I also joined them when I was there. This is to detect the movement of, we have detected an area of instability soil slopes near the river of Skelda by installing the fiber across near the dike. And I would like to share this one particular work by the Public Research Institute of Japan. There's one landslide here, which is quite large, 1.5 kilometers long with 500-meter wide, which they measured something like a meter of movement over the year. And the area is quite large, and they have decided to focus in one small part, section there, where they actually laid down a cable of about 2 kilometers long in the grid pattern, as you can see here. And one part there, they also included 3 anchors using the FBG system. So this is the diagram. I mean, the photo of the site that they installed. It's quite gentle, actually. It's quite just a 10-degree slope, but you can see here it's very wet, heavy rain season with snow melting. And this is just to show you this very simple cable laid down in the trench. One of them is anchored, and the other one is just laid it freely. You will get some readings like this. As the ground move, you can have the points actually increase due to the movement of soil. And the other one is giving you a reading which is much more gentle. This is just to show you the example of having point fixing and also freely installed inside the ground. So if we want to talk about the cable lying downwardly, we can have an idea of measuring the cracks in the slopes. So we have conventional system, electrical base sensor. This is quite expensive, crack gauge. But if we have fiber optics, we can obviously distributed system. We can just use simple anchor points, which can detect multiple crack locations, as you can see here. And it's quite, in theory, it can be quite cheap, because the cable can be as cheap as, for example, 5 meter per ringgit, and you just need a clamping system, as shown here. So that was done. That was the idea, and one work done by Public Works Research Institute of Japan. That's one slope in National Highway number 19. They actually install on the surface, and the fiber is actually inside PVC pipe, if I'm not mistaken. And they install in the zigzag pattern on a slope that is actually about 30 degrees, quite steep, over a kilometer long and 300 meters high. And there's one location where they found incident of surface, I would say erosion or surface landslide. And this was due to the typhoon. At one incident there, and it was able to, the fiber optics able to detect the movement there on 2 incidents. And when they actually check on the area, it actually confirmed the location. So as I mentioned just now, if we measure the strain, the movement in the downward manner, we actually can interpret in the movement mechanism of the landslide. This is just to share with you the idea. Where if you have landslide, the slope near the crest is actually the top part of the landslide. This is where you have a separation or extension of soil, which can cause the fiber to get experience of positive strain. And below the landslide, we call it the toe, where you can get basically compression. So this is the profile of the strain when you install in the downward manner. And then you have other mechanism of landslide. Tensile crack give you just one peak. Rotational failure, you have that diagram which I just showed. And translational failure, you have just a simple constant strain across the area there. Right, now I'm going to move to one example of how you measure in the underground, which is on the subsurface. Normally, we use a standard inclinometer probe. This is a kind of like accelerometer, which is actually attached with 2 pairs of rollers. You can see here that rollers is basically to guide the probe inside this casing. So this is a plastic tube casing, which is actually being, before they install this plastic tube inside the borehole, they will have to do a borehole drilling, and then install this casing. And then they have to fill up the opening with cement bentonite grout. And after that, once it's casted, it's stabilized, then you come to the site to take the reading to know what is the deflection of the pipe. So these are actually kind of like manual reading. And there's a groove here, which is the place where you guide the wheels of that. So the problem with this system is that it's a manual method. It requires measurements. Actually, it measures, this gauge is about 0.5 meter. So you get a reading of every 0.5 meter. So the idea is now is probably we can use fiber optic system, but we actually have to modify a bit, put the cables, install the cables outside of the pipe and measure the deflection of the pipes. So using simple engineering mechanics of Euler-Bernoulli beam theory, we can actually measure the deflection, the strain on one side and the tension and compression side, and convert that into displacement. So with that method, we can actually overcome the problem of needing to inserting the probe inside the pipe for manual reading. So it is kind of like quite cheap in a way, and it can measure both the axial and also the deflection of the pipe. And you can use the same pipe to measure the groundwater height if you put some kind of perforations below at the bottom of the pipe there. So we actually done this. We explore, we fabricate the pipes to create the groove where we can slot the fibers outside safely. And an experiment have been conducted in the lab, and also we measure the compare with the conventional inclinometer probe, which actually give us kind of like nice reading, which is almost similar to the conventional system. So you can see this is actually in our lab that we perform this deflection test. And also, but to get the deflection, you require some kind of data processing, and it's actually been done through a software that we developed. So this just to show you some of the photos of the installation of the slope. And also one project which we did in collaboration with one contractor of a project related to, this is not related to landslide, but it's related to underground works, where they have to install sewer pipelines below railway track in Ipoh. You can see these micro tunnel boring machines. They have to cross this railway track below, and we actually need to do the monitoring of this crossover below the track before they reach to the railway track, so that we know how much the ground actually moved. If it moves too much, we can say to the contractor that you have to change the construction method, or maybe improve the ground condition before you cross below the railway track. So we measure that, and as the machine actually coming closer, we can see some kind of changes in the ground related to how the pressure is being caused by this tunnel boring machine. So I will not talk about this much. And also we did some work together with Gamuda on a project related to the MRT line 2. This was actually where they have to bore through existing building below government housing. This is in Kampung Baru. This is the drilling rig with our pipes. And also we got another example of application of monitoring deep excavation of station box in Bandar Malaysia. As you know, this is the open excavation causing the wall to move into that. So there's a pipe here which we measure the ground movement. Normally we can install also along the wall, but this wall has been constructed earlier, so we just measure behind the wall. And also the measurements from the standard chronometer also give same readings. And I had this opportunity before when I back in Cambridge. This is one work in London where we installed a second firewall inside the reinforced concrete, and also to compare with the inclinometer. And this work was already been published. And the idea is very simple. Rather than you install in the pipe, you attach the cable directly on the steel cage of the pile. So this is the steel cage for constructing these board piles, right? So they have a steel cage, and we just clamp the cables. Of course, the cable have to be a different type of cable. It has to be strong and clamped on two sides. And then the contractor actually lower down the cage, and once it reaches to the top part, we actually clamp the opposite part here, and then to pre-strain it a bit, and then carry the cables to the top. And after that, they did the concreting work. And once the cage has been casted, the pile has been casted, we are able to measure the movement. And these are actually the readings during the excavation of the basement, right? So you can start to see the strain on the opposite side of the pile, this is very important in understanding the movement of the wall. You can actually correlate this to the stresses behind the wall. And we have measurements comparison with inclinometer. We can measure the curvature, we can measure the inclination, and also the displacement. And the displacement is quite small. In fact, if you look here, the reading is about 8 millimeters at most, or 10 millimeters. So what it means is that from the naked eyes, we cannot see the movement, but actually we can detect that quite accurately of the wall movement. And there's stringent requirements of the when you do construction next to a wall. Let me just show you this photo again. This is a building. Someone's actually living in this building, and you are actually excavating down to about 10 meters or 15 meters below, and the wall move about maybe 10 millimeters. So it's quite small, and you cannot see that, but it's able to detect quite accurately. And for engineering application, we can do kind of analysis for the consultant to verify their design parameters. Right, and there's other application for fiber optics. This is to integrate with geotextile. This is one work that I've been involved in Belgium. And also they integrate with GeoGrid, for example. Right, so for this is one example, we call this the engineered slope. Means that especially in the mountain where we have to build roads, we have to create embankment, and it has to be reinforced with geotextile or GeoGrid system. The problem with this is that we do not know what is the stresses in that inside that earth system. So by having fibers inside, it becomes like a smart system where you can tap in and measure the strain and compare that with your model, your computer modeling. And this one work here for the excavation of the shipping lock, where you allow the big ships to go. And here, where they have to have a double gate, 2 gates here, the sliding gate. And over the time, when we do deep excavation, this is 30 meters deep, the problem is that this soil below tends to want to move upward. We call this ground heaving. So over, like, for example, tens of or 100 years, there will be a problem of building up of pressure. And if we have the gate here, that needs to close, but then there is actually movement below, it will cause a lot of problems. So that's why we install these sensors below the gate. So this is actually the construction process, and there was actually another sensors being installed below here. All right, so there are other applications for slopes. This is for embankment and levee, especially to detect not just movement of the ground, as you can see here, but we also have the potential of measuring the water infiltration using temperature sensing, or DTS. Just want to show you the idea there. And also we have the ability to explore this application to monitor the movement of the earth embankment, as you can see here. Normally when at the edge of this embankment, there will be some kind of ground movement. If you lay down the fiber inside during the construction, for example, you are able to detect some kind of stress changes or strain changes there. I mentioned about the use of fiber optic to measure the soil nails. This is one example of that. The idea is that you can able to detect, estimate the passive stresses or the active zone where the soil nails are acting. In engineering, in geotechnical engineering, we actually are interested on how much the strain or the what we call that, the friction that is left on the one that is behind the active zone. That is where this is the one that is have the capacity to hold the slope from movement. So there's some work by some our Chinese counterpart, which they use. In this case, they use the FBG sensor to attach to the soil nails. And I had the opportunity to also work with our friends in Indonesia. There is one old landslide which caused a lot of problems to this highway, which is connect between the city of Semarang to Ungaran in Central Java. You can see there, this some photo and the bridge. So it's actually caused a lot of problems. In fact, it's so bad that the deck of this bridge has been touching the frame of this, and then and also causing a lot of instability, and a lot of remediation had to be done to strengthen the pillars foundation, as you can see here. So they have to do, I think they cost a lot of millions to monitor, and there are actually some cracks on the pillars, and we use surface adhesive sensor to measure the extension of these cracks. Right, so this is just to show you some example of different system, conventional system. Normally for landslide, we use robotic total station to measure the surface movement. Of course, it detects displacement over an area, but it will depend on number of prism, and to make it automate, this has to be a robotic total station. So it's quite expensive. And you can use also wire extensometer, but this is very localized. And if you want to measure over wide area, it's also not cheap. So we can probably try to propose using distributed system if the area is quite large. So I've done some kind of calculation. If you are, in fact, for inclinometer, if we have many boreholes, the price for using distributed system, which is the orange color here, actually does not rise up. It's quite stable if we include the price of the interrogator. Otherwise, we can use the conventional system for number of boreholes that is less than 2. So in conclusion, we can see that I've presented the overview of the distributed system for slopes engineering application. And you can see also there are many issues concerning to the stability of deploying the sensor, particularly concerning to the installation of the layout, how you protect the sensor, how you try to compensate any errors in the reading, and so forth. So there's actually quite a lot of advantage using sensor, and especially when you can embed the sensor in the structure or in the soil, so that we can get the reading of actual performance of the system as compared to the traditional systems such as the geodetic sensors, where you can only measure the surface movement. So I think I've covered generally the idea of that. I'm quite happy to listen to any of the audience. If you have any concern, I'm happy to answer. So with that, I would like to hand over this back to the chairman.
Okay, thank you, Dr. Sham. It is a very interesting presentation you just given just now. So I would like to open this floor to the participants. If let's say if you have any questions for Dr. Hisham. Any questions from the participants for the attendees? Okay, we have one from Fairuz.
Assalamualaikum, Dr. Hisham.
Ya, baik.
Just one quick question. Of all the system that we've been doing so far, you have to install a new fiber, is it?
Yeah, it's the same for any kind of instrumentation you have to install.
Is there any plan or any study we made to use the, for example, you have a telecommunication fiber running along railways, right? Can any study be made to use that to monitor the stability of that track or not?
Yes. The only thing that I didn't mention here because of the time limitation is another system. We call it the distributed acoustic system, which measure the acoustic signal or the vibration. I'm not sure if the vibration is correct word. It's like a geophone. There are already companies who actually monitor the track integrity or the movement of the train by using the existing by using the fiber optic cable that is laid along the railway track. So there are actually already application of that. Basically, it measures the vibration of the track from the running trains, but not actually to and also any kind of third-party intrusion.
So there will be a totally different system than the one that you are presenting.
Yeah. So yeah,
a different concept of optic side, different concept around that.
Yeah. They call it like how to say, it's detecting using sound, something like that.
Thank you, Dr. Sham.
Okay. No problem.
Okay. Is there any other questions for the participants? Ada? Okay, I think I have one question, Dr. Sham, because from the presentation you have given just now, it is quite interesting to see that the academicians like you can get involved or convince the industry to what you call to seek for your expertise to solve some of their problems. Maybe you can share with us how do you manage to get involved or to participate in such problems faced by the industry?
Okay, right. The question is how we try to get quite good collaboration with industry. Maybe it depends also on the nature of the area that I'm working with. So civil engineering is highly involved with construction works, and maybe the fact that we have to understand the issues faced by the industry. So we probably have to go and see them and also meet them and try to understand what they have. At the same time, we also have some kind of technology that we want to explore with them. So it's quite how to say, you have to, I think I remember last time I used to go to KL like every week to see some clients or maybe to see some companies to to try to pitch the idea. So it's quite a long process before they try to accept. Sometimes some of the project that we got involve how to say, a proposal that has been laid them for like 2 or 3 years before. So you have to do like continuous effort. Maybe you cannot get now, but maybe we can get later.
Okay. Okay. I think we have reached 10:40. I would like to give our great thanks to Prof. Hisham because his willingness to give the presentation today. The sharing session is very fruitful. We get a lot of information from you. Some of the information is quite new to most of us. And then we see that actually Malaysia is not a lack of local talent to solve some of the issues or to bring, to introduce new technologies to the industry. So thank you so much for your willingness to present this morning. And then maybe we can go to the next session. If let's say you have anything to say, Dr. Hisham, for the last time, before we proceed to the next session.
Yeah, I just want to say thank you for having me to the conference here, and thank you again.
Okay, thanks. Okay, for the next sessions, so we have a keynote speaker. I would like to introduce to you our next keynote speaker, which is Prof. Haris Ahmad. He is a distinguished professor at the University of Malaya and also the director of the Photonics Research Centre. Not only the director, he is also the founding director of the Photonics Research Centre of which is one of our high COEs. Okay, Prof. Haris obtained his PhD in laser technology from University of Wales in 1983 and began his academic career at the in 1983. And he is currently the director of PRC at the same time, which is also the high COE of the Ministry of Higher Education. He has been recognized for his substantial contributions in the area of photonics with multiple awards, including as Fellow of Academic Science in 2006, Malaysian Tourist Science Foundation's Award in 2007, Merdeka Award for Scholastic Achievement in 2010, Asian Outstanding Scientist and Technology Award in 2014, and also, just like I've mentioned just now, Distinguished Professor Award from Ministry of Education in 2014. He has published more than 500 articles in ISI index journals and supervised quite a large number of MSc and PhD students. He is currently engaged in a project involving the use of FBG and 3D printing technology for landslide monitoring, which is funded by the Newton-Ungku Omar Fund. So without any delay, I would like to invite Prof. Haris to give his presentations now.
Thank you, Chairman, Dr. Faisal. First, let me check. Can you hear me clear?
Yes, Prof.
Okay.
Yes, can.
I will share my slide. I hope I can share my slide now. I'm old school, not very well versed with a computer. Okay. Can you all see the slide now? Faisal, can you see the slide?
Yes.
Yes.
Okay, what I'm going to talk this morning is our progress on the, as mentioned by the chairman, he's also a co-member of this project, on the progress of Newton-Ungku project on devices for landslide application. It's more of trying to complement. I think Professor Hisham has given a very good presentation, the actual implementation of landslide monitoring. What we are doing here is slightly different, is to complement the first. If you look at the value chain, we are the first part, trying to look at the devices that we're going to use for landslide monitoring. And then I think we're hoping to work closely with Professor Hisham, and then we're going to field tested this landslide that we make in the laboratory. Okay, the title of my talk is Recent Progress in Newton-Ungku Fund Landslide Project. That is myself and Dr. Muhammad Faizal. We have our student, Muhammad Shamir bin Muhammad Sa'ad, Muhammad Ashraf bin Alias. I think our student will also give a much detailed presentation on the work. I will just run through what we have done, just to discuss the progress. The content of the slide will be just to share with the audience. This landslide in Malaysia is very important. I think we are going through a very serious climate change, and you find that we have extreme weather. And of late, you find you have serious flooding in Germany, in Europe. You hardly heard of this for quite some time, but you have this year very serious flooding, and also in the United Kingdom, where Professor Hisham come from. And also in China, you find China has serious flooding, and you have heavy rainfall in the Middle East. So climate change is affecting the rainfall, and also will give us extreme weather, extremely hot weather and extremely cold weather. So when we have heavy rainfall, one of the most major event that take place after the heavy rainfall is landslide. And landslide costs life. You lose life actually. All right, and then you also lose buildings, and you also lose property. So it's a very serious matter. I think it's very important for us to have more people trained. I think in this country, according to Dr. Faizal, we do not have many people trained in landslide monitoring. Not many people are very well versed. I think we have quite a large number of audience today from DBKL, the one the Bandaraya Kuala Lumpur. I mean, KL always suffer some form of landslide. I think it's quite a serious matter. I think we need to produce more manpower in landslide monitoring, because this will be a major issue in many years to come actually. So the next part of my content will be limitation on conventional method, what we have discussed. I think Hisham has done quite a very good comparison with the current conventional method. And then I'm going to share with the audience on the objective of the project. Why are we doing this project actually? And then we were going to share with you our published work in this project so far, and the current progress, and we're going to share also future work for future students who would like to join, who would like to venture into landslide research. Landslide research is very interesting. I think it's a very new field in this country, although landslide has been happening for many years in this country, but it's still, we do not have the right number of manpower to do very serious monitoring and also mitigation. We have to mitigate when we have landslide. How do we have an early warning system? If the rain comes in, can we predict when the landslide going to happen? How long will it happen? 1 hour, 2 hours, 3 hours, we should be able to predict. If we are given certain time frame, let's say 3 to 4 hours, is more than enough to move people away from the place that's going to take place landslide. I think it's a very important prevention. I think we don't want to get ourselves caught like what happened to us in COVID-19. We cannot even make our own vaccine. I think it's quite embarrassing after spending billions and billions of dollars, ringgit, Malaysia for research. I think we do not focus on how to make vaccine. I think this is the shortcoming of our research program actually. Now, landslide in Malaysia, I want to share with the audience. There are so many landslides. I think I will fill up my whole talk if I'm going to talk about landslide occurring in Malaysia. I'll just take 4 examples. Landslide at Tambun Resort, November 2020, recent. You have 2 people die. One of the 30 landslides that occur on Fraser Hill so frequently, 30 vehicles crash, and then I'm quite sure there are some deaths there. And landslide at Kinabalu National Park, 791 people from 217 villages displaced. Landslide is something that we should not take lightly at all. And soil movement at Pasir Mas, Kelantan, 5 houses damaged. So these are the things that we have to put our act together to monitor the possibility of landslide taking place. I think we have to monitor very closely. All right. Now, the current limitation on conventional method, I think, has been discussed just now from our first keynote, our earlier keynote speaker from UTP. The current limitation are mostly based on electrical system using wire. It is prone to lightning strike because you have conductor. Definitely, lightning will strike on the conductor. Low stability and durability. And it can be expensive, cannot be transmitted over long distance. It has a large scale slope monitoring cannot be achieved. You cannot do by using copper. And you also will encounter with electromagnetic interference. And there are instances that you will get shocked. Okay, that is the current limitation of the conventional slope monitoring system based on electrical technology. Now, the objective of this project, which was funded, is a collaborative project with University of London, and Optoelectronic Research Centre of University of Southampton, our UK partner, which we have invited for this conference. They are very good speakers, extremely good. You should have listened to their talk yesterday, very interesting. Professor Ken Grattan, a world-renowned figure on sensor technology itself. You have Aziz on the modeling, and you also have a very brilliant chap, Professor Dr. Banto, on the new approach of landslide, of how to monitor landslide. And interesting chap that we managed to invite in the afternoon is Professor Lugui. Okay, right now, if you look at his talk yesterday, he's looking at how to detect COVID-19 using optical fiber, tapered fiber. We are doing tapered fiber here. I think this is one of the projects I would like to initiate with Dr. Faizal, how to detect COVID-19 using tapered fiber, because COVID-19 is a very hot topic for getting funding actually. So the objective of this project to develop an optical-based sensor for slope and ground movement monitoring, to package this sensor ruggedly for the use in harsh environments and deploy for real field testing. And this we hope to work and hope to get cooperation from Hisham, because we need to use his test bed to do real field testing. We do not have that in our laboratory. We are mostly optical people. To develop an early prediction remote monitoring landslide warning system. This is very important. It means that it's a system, it's a landslide system. So if we have a sensor, we should be able to create an early warning system to warn the people around the slope to move away, as to save life. The most important thing is to save life. And then the next important thing is the properties. Now, published work. In this work, we started about, I think, roughly about 8 months. We started about 8 months on this work. We have 2 students, as I mentioned, Ashraf and Shamil. They are doing their master, but hopefully they can convert to PhD. I think they should be able to finish their PhD by end of next year. I'm very confident. And during that period of time, we have published quite a numerous work in good journals, IEEE Sensor and Sensor Actuator A, and I think we have a few more in the pipeline. So we tend to focus more on publication actually. All right, so we have published work on tilt sensor based on an embedded 2-mode fiber interferometer, which I will discuss very briefly because Shamil and Ashraf will discuss in greater detail. And the second work that we have published is 3D printed biaxial FBG-based tilt sensor. It's a very simple idea. You find it's very interesting to implement to measure the slope movement. And the next paper that we have published, 3D printed biaxial FBG-based inclinometer, and then the last paper that we have submitted, still waiting for response, which I think we should resubmit somewhere else, Dr. Faizal. 3D printed strain sensor based on embedded fiber break rating. I think we have 2-3 more that we have not completed and should be sending out soon in this couple of weeks. Now, tilt sensor based on an embedded 2-mode fiber interferometer. What we do, we have it's quite a straightforward idea. We have a single mode fiber. Typically single mode fiber has a dimension about 9 micron. It has a diameter, the core diameter about 9 micron, and the cladding diameter about 135 micron. Normally for single mode fiber, the core refractive index is slightly higher. The word I use slightly higher as compared to the cladding diameter. Why you have this? It comes back to basic physics, because we have to work on total internal reflection. Total internal reflection can only occur when light travels from high index to low index. When that takes place, the light is being trapped in the core, actually. The light is being trapped in the core. All right? So the light will not escape from the core. If not, you find the light will be escaping because it's made of glass. It's made of transparent material. The light will just escape all around it. So we have to trap the light. So the light is being trapped by simple physics idea, having the refractive index of the cladding slightly lower compared to the core. The next component is quite a short length of 2-mode fiber. Now, what is 2-mode fiber? Normally a single mode, SMF, single mode. In this fiber, only one mode will be traveling. That is given by LP01, only one mode. And then we have another fiber, 2-mode fiber. The 2-mode fiber is the same as single mode. The only difference that you have is the core diameter is slightly bigger. The word I use slightly bigger, it could be 12 micron, 13 micron. So by optical fiber technology, by optical fiber understanding, when you have the core slightly wider in terms of diameter, you will have more than one mode traveling in the core. So when you have 2-mode fiber, you virtually have 2 mode that's traveling in the core. The 2 mode is LP01 and LP11. They will travel in the core, and then it will meet up again at a single mode fiber that will only allow 1 mode to travel. So 1 mode goes in, convert into 2 modes, and then it comes out as single mode. When you have 2 mode traveling in the 2 mode fiber, you have interference taking place. A basic physics that you learn in school. Interference takes place because you have 2 light at different frequency. So normally if you look at the next figure, you find the interference pattern being formed. Now it has a shape because this shape may follow the gain profile of your light source that you may use. All right, so you look at the fringes forming, very sharp fringes forming. All right, these are called interference pattern. These are the typical structure of 2-mode fiber interferometer. In short, we call TMFI, showing the single mode fiber and 2-mode fiber section. So how do we mount them? We have a 3D printer. We make housing, okay, and then we have the single mode fiber and the 2-mode fiber here. And the single mode fiber is being embedded into the structure, and then on this side, and the 2-mode fiber is being left in the space. So any tilt, any bending will cause a change in the interference pattern. By detecting the change in the interference pattern, we can more or less precisely tell the tilt angle, what has taken place, what are the strain force that has made this change. And these are the things that I think Dr. Hisham have discussed this morning. All right, it's a very interesting talk. It's an eye-opener to me, myself. And this is how we normally implement. So you have the light source. We normally make our own light source. It's called the amplified spontaneous emission. We use erbium doped fiber. We permit and to excite them into higher state. Eventually, it will decay to lower state and give out lights spontaneously. It's not a laser. Please be careful. It's not a laser. It's just a light source spontaneous emission, because we don't want to use laser. We want to use a broad light source. So the ASE comes into the optical fiber. The signal comes out from here. If the tilt takes place on this second figure, the tilt takes place. And then you will observe the changes in the interference pattern as given in the bottom figure of this slide. That's how you, by measuring the displacement, or by measuring the change of the pattern, I will know precisely the tilt angle that takes place. If I have any soil movement taking place around the two-mode fiber, so any soil movement taking place at this part, it will cause a bend. It will cause a bend. By causing the bend, create a strain or a force onto it, I can detect precisely the change of the fringes. From this, I can tell precisely the force that is taking place. So soil physics is very important, because we have to understand soil movement comes at what part of the soil actually. Is it the upper part of the soil, the middle part of the soil, or the bottommost part of the soil? Which part the soils begin to move? Eventually, it will create more movement as it moves towards the upper surface. So this is very interesting to know exactly at what position of the soil that really move actually. So the 3D printer sensor, we do by 3D printer, it looks like this. It's very nice. It's nice and quite simple to do. I think every student can also venture into this area, because 3D printer is very useful to make product and to make devices. Now, I will just go through briefly on the principle of FBG. This is the second paper that we published, 3D printed biaxial fiber Bragg grating based tilt sensor. I will just go very briefly. Now, fiber Bragg grating, how do we make fiber Bragg grating? We use 2-photon absorption actually. The physics behind that is 2-photon absorption. So we have a UV light. You need a very short wavelength light. Normally it's UV 244, 246. You can use them. It's from an excimer laser. We have the laser in our laboratories, and we make our own FBG. We don't buy them, but sometimes if we need in the rush, we do buy from China. They are very cheap, but we make ourselves. We have all the face masks and all wavelength that we want to do, from 1.5, 1 micron, 2 micron. We have all the face masks to make FBG at different wavelength. So you just imagine now from this figure, you have the white area is the core, the shaded area is the cladding. So what we do, we take the UV light from an excimer laser, and we focus it exactly at the core, not at the cladding. We focus it exactly at the core. And then before the light goes into the core, we have a face mask. A face mask is just a pattern. The pattern plus, minus. It's just a pattern, interference pattern actually. So we put masking. We mask the pattern onto the core. Eventually, you find that we can create a slight change. The word I use is very important. A slight change in the refractive index. It's very small change, but it's been done repetitiously. You find that this pattern, maybe there are about 100 patterns formed in the core. So when you have an incident light that comes in, a broad band light, like amplified spontaneous emission, normally we use an erbium doped fiber to create the broad light. When it comes in, it will see the first change of the refractive index, and it will partially reflected, only a small percent, 1% will be reflected. And then it comes again to another boundary, another refractive index change, and then it will be reflecting again 1%. So 1% becomes 2%. And this process will be repeated until you will get a sharp peak at Bragg wavelength being reflected. So the Bragg wavelength depend on the spacing of your fringes here, the spacing of your changes in the reflective index. There's a spacing between one point to the next point. That's called the Bragg wavelength. And then you will get the reflected light at maybe 1552. Very sharp peak. This light will be reflected. And the rest that is not being reflected, you look at the broadband, the rest will not be reflected. You get the transmitted light with a sharp dip. You get everything else but except a missing part. There's a dip here that is this reflected light here. So using this simple principle, what happened if I put this FBG in the soil, any strain, any soil movement will create a pressure onto the fiber Bragg grating. And this will cause some displacement, and it will cause some elongation taking place, and it will stretch the fiber slightly. When you stretch the fiber slightly, you find that the spacing of the reflective index that you formed earlier will also change, very small change. And then you will detect, instead of having this wavelength at lambda 1, 1552, you may get 1553. So there's a change of wavelength now. That change of wavelength, about 1 nanometer, you can tell precisely the strain or the pressure that takes place, the soil pressure onto your FBG. You can tell precisely. So it is a very accurate method of detecting your soil movement. All right. Now, this is what we have on the spectrum. If you look at the of the upper figure is unstrained FBG, you get a very nice spectrum. And then when the FBG is being stretched, the word I use stretch is being pulled apart, you find that the FBG peak wavelength will be shifted slightly now. So that shift will tell you how much stress or strain has taken place on your FBG. So this approach of using FBG is very interesting. It's not influenced by electromagnetic noise. That is a very important point. Free from electrical problem caused by insulation. If you use electrical system, you get that the insulation, the plastic will give way due to the moisture, the water. But using glass, you find it's inert. It's purely inert. You do not have any deterioration taking place onto your glass structure. 2 or more sensors can be connected in series. You can do multiplexing. You can have 100 sensors in one line. So you can do 100 sensing point actually. And it's very cost effective. And if you look at the FBG that we have made, I think this is the actual, you look at the second figure, is the actual device how we make. We use red color. It looks very attractive, red. Of course, you have other color, blue, you can make them if you like. And in this system, we have FBG at 4 corners, and we have additional FBG as a temperature sensor, because when you have temperature change, it does affect on the FBG. So you have to compensate any temperature change. So we have another FBG to measure the temperature, which will offset the change in the wavelength due to the change of temperature, will offset the 4 FBG change of temperature. You only detect the change due to strain, that's all. So this is a very intelligent system. We offset any other parameters, so you only detect the strain measurement. This is our tilt sensor designed by our student, Ashraf and Shamil. They are very clever people, extremely intelligent. And this is a real picture of the tilt sensor, because the work is being done by them. I do not know very much about this, because my field is actually optical fiber. There's fiber devices. So our student is very good. I think they are so much clever than me. Now, if you look at the working principle, if you find that if your fiber is being compressed, if you look on this side, on your left hand side, is called the FBG X, the fiber X. There are 4 fibers there. It can cause strain, and on your right hand side you have FBG plus X, another fiber which we call plus X, and then it will be compressed, because when you stretch, if you apply strain on one end, the other end will be compressed, and that compress will cause a shift of wavelength. The strain itself will cause a shift of wavelength, and that will be translated into a result given by the next figure, the output of FBGX. You can see the change of the wavelength by measuring the change of the wavelength. You can tell precisely the strain that takes place in the device. Now, the 3D printed cover, I think we sent the paper for publish. One of the reviewers asked us to do some modification to make a casing as to protect the FBG sensor. So we have a casing, a schematic design of the cover printed as 2 parts using 3D. Everything has been done using 3D printer. Now, the other paper is on 3D printed biaxial FBG based inclinometer. Is given as in the rear figure. Also red, I think our students love red color somehow. They like red very much. They love red color. I think you must understand the bull fighting. They see the red color, they will charge on you. But actually, bull are colorblind. They cannot tell the difference of the color, but because the cloth is smooth, they get excited, they will charge on you. So normally red tend to have a very attractive color. You find the red, Ferrari and so on. So the student may have choose red because they love the color so much. So red picture of a tilt center attached to a pipe connector. If you look at this, is the top view. So the FBG are being placed at your X minus, another FBG at X plus, another FBG at Y plus, another FBG at Y minus, and somewhere around the tube you have the FBG for measuring the temperature. Now, this is what you will see in the actual field, which we hope to test with Professor Hisham, but we couldn't do because of COVID-19. It's very unfortunate, but we hope to be able to travel within the next few weeks when we move into phase 2. So, as explained by Professor Hisham, the standard inclinometer casing is just given as PVC pipe, and then you have a wheel, and that is another PVC pipe. Then this thing will be slot into the ball. It will be slot into. You will push it inside, and the same thing can be done using FBG. We also have designed the casing, and this is our FBG sensor, the inclinometer that I've discussed in the last few slides. It will be slotted into the ball as given into this figure. This is the actual figure. This is the actual real picture of the FBG inclinometer. Okay. Now the next paper that we produce is called strain sensor based on embedded fiber bright grating in a thermoplastic polyurethane TPU using 3D printed technology for improved standard. This one, you find the FBG is being covered by material thermoplastic. All right, the FBG inside here, and then you find the TPU, the filament, the one that we use to make the 3D printer. Eventually, you can put the whole FBG with protection from thermoplastic onto your pipe. And the key behavior of this approach, it has an excellent tensile strength. It has somehow amplified the tensile stress, robust to weather and UV resistant, and good flexibility over a wide temperature range. This is a very innovative approach. So the experimental result that we have done, which I did mention just now, will be explained in depth by Ashraf and Shamil. So by having a strain, I will see the shift in the wavelength as given in the red. The red is the bare fiber, and when I put the thermoplastic, I will find a slight shift. It gives embedded FBG. The black, it has some slight shift. But if you look at this graph, interestingly, look at this graph. The graph number 2, And when you put the FPG into the thermoplastic, it has a better slope, improve the performance given in black line as compared to bare FPG. So by using this approach, you have an improved performance. When you have improved the performance, what does that mean? It's more sensitive, so that any changes you can pick up very fast. It's more not sensitive. Now, these are typical what we have in the laboratory. Right now, we have optical spectrum analyzer. We have quite a number of them. And we have just in the process to purchase an interrogation system. We have 2 or 3 with another colleague, Dr. Lim Koseng, but we are buying another set interrogation system that going to be deployed in the field. We cannot bring the OSA into the field. They are quite expensive, and then they are not hardy and not robust to take the extreme weather in the field. So we have to use an interrogation system. These are some optical equipment, laser diode, and so on. And this is how we do the temperature testing. And the 3D printer is behind here. You can see the white box there. And this is how it looks like. You have the free end, you have the fixed end. So this is how we do the lab testing. We fix the end and then we bend from the top. Then you find that any bending will make a shift, and then you can do so many experimental results according to the temperature, change of the temperature, and so on. These are the typical measurement that we got between the wavelength shift of the signal and the horizontal displacement of the FPG. This will be discussed in the coming session. Same thing, we do temperature. It's very important to calibrate against temperature because FPG will cause a change of wavelength due to strain and also temperature. Large thermal expansion of the TPU film induces the strain on the FPG to be more sensitive. It can be made suitable at temperature ranging from 25 degree to 50 degree. We calibrate until 50 degree because of the climate change. We never know, Malaysia may experience 40 degrees like in the Middle East in next few years. Therefore, it has been demonstrated that the embedded FPG sensor can be used effectively in measuring strain with high accuracy. We stress the point here, high accuracy. So this means that this inexpensive 3D printed FPG based strain sensor can be further developed and used in a most stable manner for lens-like monitoring, structure health monitoring as climate change keeps on getting worse each day. And the current progress that we are doing work on extensometer. I think Professor did mention, if I'm not mistaken, just now. Also, some work on the vibration sensor is very important to see the seismic wave. In the ground, you have wave underground actually. So we want to create a sensor to detect the ground wave actually. It's called the vibration sensor, FPG based on FPG based Fabry-Perot interferometer. And these are the work that we are doing. If you look, this is done by, if I'm not mistaken, by Ashraf, FPG based strain sensor, where the FPG have been placed quite a number of them along the pipeline. Any bend of the pipe can detect the changes of the bending by the shift of wavelength in the FPG. It's a very inexpensive 3D printed extensometer for ground displacement monitoring using fiber bright grating technology. And this is the lab experiment that we are doing, splicing of multiple FPG based strain sensor, as going to be discussed shortly by them. And these are the same thing what we have been doing. If you look, the pipe is being slightly bent, and that's how we measure the bending of the piping by measuring the shift of wavelength. Now we are doing work on testing ground movement. So by using the extensometer, we can detect the ground movement, And these are 3D printed extensometer holder using 3D printer to hold the pipe in place. And the next is vibration sensor done by Shamil, FPG-based February interferometer. Prior to any landslide, the soil structure will change actually, and this will cause seismic vibration inside the soil. It's important to monitor this parameter in order to develop landslide early warning system, because we want to come up with a system, early warning system to warn the people. It's no point to measure when the landslide going to happen. It will happen. You cannot avoid landslide from taking place. That you have to remember. You cannot avoid. Okay, so what we want to do to have an early warning system. So by doing this vibration sensor, we can detect earlier the movement of the seismic vibration. We are currently developing a temperature-independent vibration sensor based on FPG-based February interferometer. And this is what we have done. This is what we measure. This is not what. This is how you measure, taken from one of the paper here. Okay, the data shows that landslide occur at low frequency region, high in magnitude. So this is our experimental. I will not go through into detail. I think Shamil will discuss this further. It's quite a simple setup. You can look at this figure, and that's how we set a burst of low frequency signal, and from there we can detect the wave, the seismic wave. And future work that ASAP is doing is having tilted FPG along the pipe. This idea was given by Jibato to see to get a better all around. Meaning if I put a pipe, I can detect movement of soil around the whole pipe, not only in one direction. I can detect in every direction. So these are twisted FPG, which we are undertaking now. These are typical results that we are doing now. And the FPG-based pressure sensor for soil mapping. We are also doing this for soil mapping. An array of this sensor could map the whole pressure point of the soil and area. This is being done by Shamil, and if I'm not mistaken, I think, if I'm not mistaken, I have finished my slide. That's all, Mr. Chairman. Thank you for the time, for giving me the pleasure for the presentation. It's a great opportunity for me. I would like to thank the audience that is present today. I hope you are able to benefit from my talk.
Okay, thank you, Mr. Chair, Prof. Haris, for the presentation just now. So if I would like to open the floor to the participant, if let's say you have any questions for Prof. Haris.
I would like to take some questions. Anybody
Can ask any question.
Our Malaysian audience is very shy to ask questions. They feel that they are so worried they ask silly questions somehow. But I think we learn by asking silly questions. Actually, we learn a lot by asking silly questions. That's how we learn actually when we are young. Okay, we ask why the sky is blue actually. And these are the questions that we ask our parents. Sometimes our parents cannot answer the question. And I may not be able to answer your question also. So any question, please post to me. Prof. Hisham, please, you are most welcome, sir.
Hello, bro.
Yeah, Prof. Hisham, good morning to you.
Yeah, I would like to ask a question about the FPG, if you can actually install inside a latex membrane.
Should be. I think the idea we are also exploring, because latex is very. The one that we do is thermoplastic. Okay, I think we can install the FPG, because what I want to do now, besides this work on the landslide, I want to wrap polymer around FPG actually, and then we write onto the polymer sometime. So there are various opportunities. I think your idea is a very important question. I think Shamil, I think we will try the idea of writing FPG on the text. I think should be possible, Professor Sham.
The reason why I asked this question because in the soil lab we also test the soil samples using a so-called triaxial apparatus where you compress the soil inside a cell filled up with water, and but the soil must not actually touch the water, so that's why we actually put on the latex to the cylinder sample. So, but my thinking is that if the latex actually can be incorporated with FVG, it can measure the change of shape of the sample, which is going to give an added parameters for the experiment, for the measurement.
Okay, what you want us to do is that we will write the FPGA and then we will code it with latex. Is that what you want?
Yeah, latex is just a simple latex, but not sure if you can produce that. But if you say it's possible, then it's okay. It's a future opportunity.
I think Faisal, you can take note. It's a very good idea, and we can publish a paper on this. I think we are quite interested in publication.
Actually, the Prof. Hisham idea is quite similar to the one that you have presented just now, where we put the FBG inside the TPU. Actually, TPU is a very elastic kind of material, just like latex. And then you can shape what you call the sensor based on the requirement of your problems. So it is possible.
We hope our member, I think Ashraf dengan Syamil, also Anwar is our FBG expert. I hope Anwar is here. I think we can try that. We will try that as soon as possible, Hisham, and get back to you. Will that be okay with you?
Yeah. We can have a standard discussion later.
Okay.
Okay, right.
Is there any other questions?
So
Okay, if there is none, so I would like to thank Prof. Haris because of the presentation given by him just now. So we have another sessions after this by maybe presentations by the students and researchers from IUM, and then I think for this morning there are two keynote speakers that have given their presentation, which is Dr. Hisham and Prof. Haris. The conference committee would like to give a very gratitude to both of them for their presentations. So we will have a very short break, maybe 5 minutes before we continue with another session after this. Okay, thank you so much for everybody.
thank you, Chairman. Thank you for the time.
Okay.
Okay, bye-bye.
Okay, bye. Short break, 5 minutes. And another session will be chaired by Dr. Lim Kok Sing.
Okay. Shamil.
Yes, Doctor.
Okay, so please, I think you can get ready while waiting for other people. You can actually share screen.
Okay.
Okay, so we'll start in 4 minutes.
Prof, Prof, I change place. It's too echo.
Shamil, did you talk to me? Okay. Yeah. Good morning, everyone. Welcome back to the first International Conference on Innovative Optical Sensors 2021. So our next presenter is Shamil. So just let me read. Okay. So yeah, Shamil, can you turn it to your screen, your PowerPoint? Okay. So the next presenter is Mohammad Said. So from Photonics Research Centre, his title is 3D printed biaxial tilt sensor based on fiber Bragg grading FPG sensing approach. And you have 15 minutes for presentation, and there will be 5 minutes for Q&A. Yeah, please.
Yeah. Assalamualaikum. Very pleasant morning to everyone. Okay, this okay, yes, very pleasant morning to everyone. Thank you to Associate Professor Dr.
Shamil, sorry. I think your voice is very, very soft.
Very soft.
Yeah, very, very soft.
Hello?
Yeah, no, there's no improvement. I think you have to change your mic.
Okay.
You were adjusting your speaker. I think you have to adjust your mic.
Adjusting.
Yes, go to the max.
All right. Hello?
Maybe more, a little bit more.
Hello?
Okay, yes, perfect.
Okay, thank
Yes,
you.
please proceed.
All right. Okay, again, thank you to Associate Professor Dr. Lim Kok Sing for chairing the session this morning. So without wasting any more time, let's proceed to my presentation today. So if you cannot see my slide, or if my slide is not moving, please let me know. Okay, so the title for today's presentation is actually 3D printed biaxial 2-axis tilt sensor based on fiber bright grating sensing approach from Photonics Research Centre, Universiti Malaya. Okay, I'm going to talk about the outline of my presentation today, divided into three actually. Introduction, where I'll be talking about a little bit about the sensor, FBG background, and FBG interrogation setup for this device. Although Prof. Haris has already talked some background regarding the FBG, but I'll be brief regarding my presentation. So okay, then we go to the sensor, which is the 3D printed tilt sensor. We'll be talking about the designs, working principle, calibration due to the tilt angle calibration, and then temperature calibration, as well as the cover for the design. Okay, we did the cover for the design because some reviewer asked us to provide a cover for the FBG because FBG is quite fragile. And then the last one is we'll be talking about the benefits of the device. And introduction, so tilt sensor is actually very crucial in measuring the angular deviation of structure or plane. Okay, in this case, we can see the bridges. We can monitor the inclination of the bridges, or to the right is actually the slope. So we can monitor the slope, or we want to monitor the inclination of the slope. So this is to predict or to early landslide warning system. Okay, the bottom part is actually the currently used tilt sensor in the industry nowadays, but as various keynote speakers have been briefed on this, the tilt sensor is actually electrically dependent, and then it's prone to electromagnetic interference as well as lightning strike. So we hope by introducing optical fiber sensor, we can eliminate these limitations. Okay, and then some background of fiber bright grating. This has been briefed by Prof. Haris just now, but you can see the input from here. Okay, the input broadband spectrum, we go into the fiber core, and then we have gratings here, which inscribed beforehand, so that the grating can reflect some of the part where we call the bright wavelength. Okay, and then the transmitted part is actually the broadband source, but without the reflected part. Okay, I hope this is clear so far. And then any changes to the grating structure will cause the wavelength to shift. As you can see, the top part is the initial spectrum of unstrained FBG, what we call initial position of the gratings. And then any strained FBG, it will cause the wavelength to shift to the right. So we can calculate the rate of the shift due to the strain, and we calculate anything that related to it. Okay, then because the FBG are directly affected by strain, so we can call that FBGs are directly affected by strain and temperature, because temperature also can change the grating structure. Okay, then we move on to the schematic diagram for FBG interrogation setup. So for this device, we have a broadband spectrum. This one, okay, broadband spectrum goes right towards port 1 of an optical escalator. So an optical escalator is important because we don't want the light to go back towards this one. For example, you go to port 1, then go to port 2. Because FBG is based on the reflected part, so the reflected part cannot go to port 1. So from port 2, go straight to port 3. Okay, so the broadband source go to port 1, exit at port 2, act as a light source towards the FBG. This is where we call the multiplexing capabilities of the FBG, where Prof. Haris said we can use about 100 sensors. So depending on your wavelength separation. So in this case, we use FBG 1, 2, 3, and 4. So the reflected part from the 1, 2, 3, and 4, which is embedded on the sensor, will be reflected back to port 2 and go to port 3. We will go to optical spectrum analyzer, to which we monitor the wavelength shift, or the wavelength lah. So this one we can improve by other, if in field applications, we can use that OSA, we can replace by optical interrogator for in-field applications. And then move on to the sensor itself, which is a 3D printed tilt sensor. So this is actually manufactured by our 3D printer by using PLA material, which is polylactic acid. If you are wondering what is PLA looks like, it's actually about similar to plastic, right? Quite similar to plastic, where the middle shaft here, it can be bendable. This one. So we design it to be quite bendable so that it would induce strain to the FBG. Okay, the design here, you can see that it consists of 4 FBGs, 4 FBG to imitate 4 different directions. For example, you can see FBG1, positive X. Okay, FBG1, this one is positive X. If you can see, it's actually facing me or facing you guys. And then the FBG3, negative X, facing backwards. And then the FBG2 here, positive Y to this side. And then FBG4, negative Y to this side. Okay, this is dimension, which is it's very small actually. A total of 6.9 cm in height, and then 1.2 times 1.2. And the middle shaft is actually only 4 cm. So to the right, you can see the actual device manufactured. So the middle here is the FBG. So this one is the gratings. Okay, we move to the working principle. Okay, because this one FBG are directly affected by strain, so we should able to induce strain to the FBG so that it can cause we can get some input from it. So for example here, force coming from negative X direction. Okay, force coming from negative X direction, and then FBG, the grating that facing negative X will induce strain. Okay, this one actually I have one here. If you can see, it's actually so if you force this one from negative X, you push, and then it will cause strain here, right? Then when the FBG is undergo strain, and then you can see on this part, which is this is the initial wavelength, and then towards a certain tilt angle, it will shift to this one. So the rate of the wavelength shift related to the tilt angle, we can actually determine the tilt angle later. All right. So and here we include FBGT because for temperature compensation purposes, this one, as you can see, it does not affected by strain. So this is a free end. So whenever this one undergoes strain, this one does not. So we have a constant parameter to monitor temperature. Okay, this is the calibration setup for this device. Okay, as you can see, there is broadband spectrum here, amplified spontaneous emission. It goes directly to port 1, to a circulator just now. So port 1 goes to port 2, all the way to FBG. In this case, the FBG are spliced in array, or we can call it series formation, so that all the spectrum can go back to port 3, and then goes to OSA for wavelength monitoring. You can see the shift here, right? And you can see here there is a dead weight. This is because to induce strain. Okay, for example, if you can see on my screen here, okay, if you tilt sensor like this, for example, in the digital protector, you tilt to a certain angle, and then the dead weight will cause the sensor to bend. Okay, so for example, you tilt towards I call this positive X, and you call tilt towards positive X, then the weight will induce strain to this FBG that facing positive X. So we can expect it that we can see that the direction of the bend came from positive X direction. Okay, this is the initial results. The result. So okay, this one is the initial reading of the FBG, 4 FBG that represent 4 direction. You can see this one represent negative Y. FBG facing negative Y, so it's a 1534.1 nanometer, and then it's represent positive X and negative X and so on. So 4 FBGs, and the bottom part, it shows that when the tilt sensor is tilted towards negative Y direction. So you can see that only the FBG at negative Y that has shift. Only the FBG at negative Y rate shifted to the right. Okay, the others, you can see that no observable changes or no observable shift can be detected here. Okay, this is just we enlarge the part of the shift. So this is actually when we tilted the tilt sensor towards positive X direction. Then this is the linear linear correspondence. So you can obtain a 0.013 nanometer per degree. So for 1 degree of tilt, we can expect a 0.013 nanometer shift in wavelength. Okay, so this is the calibration due to temperature. Remember, we have an FBGT. So FBGT, we need to calibrate it to temperature to obtain the temperature compensation to compensate the value of the strain. Okay, so we put it on the water bath, then we monitor the temperature. We increase it in 10 degrees C intervals. So from room temperature of 27 up to 80 degrees Celsius. And you can see a very linear correspondence, linear relationship between the temperature and the wavelength shift. Okay, you can see that the sensitivity is actually 0.0136. So for 1 degree Celsius rise in temperature, you should compensate the value by 0.0136. That is what it meant by temperature compensation. Okay, and then the cover design, because some reviewer told us that I've said this before, that some reviewer told us how do we cover the FBG, because FBG is such a fragile material, fragile fiber. Okay, we design a cover. So this is the schematic design of the cover. It's printed as 2 parts. So this one, so when the printer is finished, okay. So the printer is finished, so you can expect it to be like this. So it can be closed down. So this is this sensor attached to the cover. Okay, and then we go to the benefits. So first, it's easy to manufacture or fabricate. This one took only 1.5 hours to print both of it. We can actually lay out 2 and then print it out simultaneously. So it's a very safe time. It saves time and cost. And then it's lightweight. It's a very light. Okay, the total dead weight here is only 20 grams. So we can expect not exceeding 100 grams per sensor. And then FPGT acts as temperature parameter monitoring. So, and then it can be attached to various surfaces in numerous engineering applications. You can see this design. Okay, you can either, it's actually, I told you before, it's PLA, it's kind of plastic. You can attach or glue it anywhere, or you can even attach a screw and then you can drill it and place it to monitor the structural health of a building or bridges just now. Okay, that's all from me. Thank you. I open up for question and Q&A session.
Okay, thank you, Shamil. So, Bob, we are open to the floor for Q&A. So any questions for Shamil?
Hi, Shamil.
Hi.
May I know, what is the breaking limit for this FPG sensor?
Breaking limit. This one is actually under progress because we know the tensile strength, right? The tensile strength. So actually testing it to limit, but up until now we're testing about 50 gram. Now it's a 20 gram, right? But it's 20 gram, it still can bend. But we can test more. After this, we can test more so that we can find the breaking point.
So the bending is actually caused by the dead weight.
Yes, correct.
So let's say you put it horizontally, so the dead weight will.
Yes. For example, like this, you can bend like this.
I see.
So it will induce strain to the FBG, top side.
Okay.
Right.
So I was thinking that there's a external environment or the soil is going to bend the FPG. It's not. It's actually the dead weight that bends it.
I see. I understand you. But for example, if we put this one onto a soil, right? So if the soil movement towards this direction, then you can actually so I can actually predict the movement, where the movement came from.
Okay, thank you.
Very welcome.
Any other questions from the floor? Okay, probably one for me. So Shamil, it's a very interesting work. Looking forward to see it in action at the site. But there's I have one concern though regarding your shop, which is actually made of one of the, I can't remember the name of material. It's actually a polymer material.
It's kind of polymer, yes, correct.
And it is also sensitive to temperature. So most polymer or any material, they are also very sensitive to temperature change. So what happens if, does it have or I'm sure it has, what would be the thermal expansion coefficients of your polymer? So in the event of temperature change, your shaft will expand. That will induce additional extension or strain to your FPG. So how are you going to, have you considered that, and how do you take this consider that in your application and measurement?
Okay, thank you, Professor Dr. Lim Kok Sing. Okay, actually, we have thought about this because, for example, if you heat the temperature too high, and then the material might be degenerate, I think. Okay, but up until now, we have tested up to 90 degrees Celsius of water bath, but the linear correlation between the tip angle and the wavelength shape is still the same. But we currently studying on this.
I think it is what you can do is you can study the temperature sensitivity of each FPG without the shaft.
I see.
And then you also study the temperature sensitivity of the FPG attached to your shaft. And you try to find out what is the sensitivity difference. Yes. So, okay. Is there any other questions? Maybe we can just take one last question before we end the session we still have two more presenters. So before we move on to the next presenter, is there any other questions? And the next presenter is M.A. Alias. So please, if you're in the...
I'm here, Prof.
Okay, please get ready.
Okay.
So if there's no other questions, I would like to thank Shamil for his interesting presentation. So I look forward to seeing your products and your prototype in actions. Okay, so next,
thank you, Prof.
We are going to have the next presenter.
All right.
So you can actually share screen so that I can see your full name and also your title.
Okay.
Wow, very pretty presentation. You use Canva, very fancy software. So I've been learning the same software as well, but it's a very, very good.
I tried.
Yes. Okay. So without further ado, I would like to introduce next presenter, Muhammad Ashraf Alias, who's currently a postgrad student at Photonics Research Centre. So the title is Strain Sensor Based on Embedded Fiber Grading FPG in Thermoplastic Polyurethane using 3D printing technology for improved sensitivity. So we have 50 minutes, and for presentation also 5 minutes Q&A. You may start now.
Okay. Firstly, thank you, Prof. Lim Kok Sing, and thank you everyone for joining. So basically, what I'm about to present is strain sensor based on embedded fiber grading (FBG) in thermoplastic polyurethane using 3D printing technology for improved sensitivity. So the thing that I wanted to highlight here is improved sensitivity, because that is the most important thing, especially in this ever modernizing world. Okay, moving on. Going towards the content. Okay, I would cover firstly the introduction of my paper, and then moving on to the objective, as well as the setup and principles, and results and conclusion. To save time, I move forward to the next slide. Okay, as for the introduction, I would want to focus on three main things, which is strain, fiber grading, and thermoplastic polyurethane, which is TPU, the material that I'm using. Okay, firstly, as we go into strain, from here, you can see that strain is actually used to describe the elongation of a section or deformation that occurs within a body. In physics, basically, fundamentally, it is a concept that I use to describe how an object or a body responds to an external load. And then from there, we can measure and collect certain amount of data that might be useful for us, especially in terms of smart monitoring. And then as we go on to fiber break ratings, I'm sure Professor Harith and Professor Isham as well as Shamil had introduced some information about fiber break ratings, but I'm still gonna go through a bit, which is fiber break rating is actually a wavelength selective filter or a series of optical filters that can return certain wavelengths. And then for the material that I'm using, which is TPU, it's actually a melt processable thermoplastic elastomer with high durability and flexibility. That is why I want to use the TPU material as the body for the strain sensor. Okay, as we move on towards the strain sensing, okay, I would like you all to have a clear idea of strain sensing first before moving on to my project. Okay, as you can see here, this is a curve, this is a pipe, PVC pipe. You can say a PVC pipe. And then the upper bending part here, we all know that it is called tensile strain. And then if it's the tensile strain, the lower part here, we will call it as compressive strain. So if you are clear with this picture, then I'm sure you have no problem following me in the next slide. Okay, in terms of explaining strain using FBG, we can see that this is the picture, and I'm sure most of our presenters had explained what FBG means and its principles. As you can see here, this is the grating of the FBG, and this is the periodic grating spacing. As you can see, when the FBG is unstrained, the reflected light is like this. It is green in color instead of red. And then, as you can see, when the FBG is strained, the grating will also be affected. The grating period will also be affected. That is why you see here, the reflected light is red instead of green. See, there's a slight shift here, probably about 0.1 nanometers, something like that. Okay, and then going towards the material that I'm using, which is thermoplastic polyurethane TPU, the reason that I want to use this substance is because it has a high flexibility and durability, which will prove to me that, which will have the capabilities to prove us for measurements at complex areas or complex structure. That will, I think TPU will make it possible. And then we can see, as explained by Prof, it is also UV and it has a higher chemical resistance. It has great thermal resistance, in which I will explain more in my graph later. It has high strain sensitivity compared to other materials. It even has high strain sensitivity compared to its normal drawbacks, such as PLA, the material that Shamil used. And then it also has greater abrasion resistance. Okay. Okay, the first picture here is actually research by Loic in 2011, in which he had produced a strain measurement of composite laminates using embedded fiber break gratings. Why he had used fiber break gratings is because it is very, very sensitive, and it can calculate and it can detect very small changes. That is the reason Loic had used fiber break grating in his paper during 2011. And then, as we see down here, this is the example of conventional strain sensor that I'm sure most of us have used it, especially students right now, because in this modern era, I'm sure students are more prone to learn digital electronic stuff, something like this. This can be translated, this can be converted, the data here can be converted inside your computer, and it can all be displayed. Okay, based on all of that, I had produced a 3D printing process of my strain sensor, in which it will look like more or less like this. See here, this is the strain sensor. Okay, we move on to the first step. First step would be design making. For design making, it's up to you all actually. You can design at any design software such as Fusion 360 or even SketchUp. For me, I would prefer Fusion 360 because it is, I don't know, it is much more beautiful compared to SketchUp in terms of the lines. And then for the printing settings, as soon as you got the design, you have to generate an STL code from the software such as Fusion 360 or SketchUp. You can even design through AutoCAD if you're used to it. And then from the design STL code that is generated, it is uploaded into another 3D printing software such as Cura, the most famous one that are most used by 3D printing people nowadays, to further edit and generate a G code as an end product code for printing. What I meant by further edit is to edit the contents inside the body of the strain sensor, such as how much thickness do I want, things like that. That can all be set inside this software inside here. And then after a G code has been generated, then we can proceed to the printing of the sensor body, in which, move on to the next step, which is the waiting game, in which most of the time I would do my other works because it would take sometimes half an hour to 4 hours, depending on your design and material that you're using. Okay, this is actually the end product of the strain sensor that I have printed, and I have used a scissor to cut this line here, cut this nicely, and I had placed the sensor nicely just like this. This is actually the 3D printed view, 3D view of the sensor. As you can see, this is the embedded part. The FBG is embedded inside here, so it is well protected. But to see, is it really well protected? So we have to see the graph. Okay, I'm sorry for the picture here. And then as for the objective, I have three main objectives, which is first to produce an alternative way in fabricating optical strain sensor, second to improve the sensitivity of optical strain sensors, and third to produce a reliable and effective strain sensor that can be made ready for any field applications, especially now during climate change. It's very important. Okay, as you can see here, this is the setup that I've used to test my strain sensor, in which I had multiplexed each of those strain sensor just like this. Just like this diagram here. Okay. And then I would, this is actually an optical table equipped with M6 step hole. As you can see here, these holes are actually 2.5 cm in distance. That is why I've put this one 2.5 cm. So I can measure the free end of the PVC pipe by 2.5 cm intervals in terms of its horizontal displacement. By then I can measure, the sensor that is placed on the outer side of the PVC pipe is surely about to experience tensile strain, whereas this one and this one and this one, which is FBG 6.2, will experience compressive strain. This is the setup that I've set. As you can see here, this is the cross-sectional view, and this is the compressive strain, and this is the FBG that will experience tensile strain here. This is the bending direction. Okay. And then this is actually for a clearer view for those familiar in optical fibers. This is actually the schematic diagram of my setup, in which ASE is connected to port 1 as my light source, and then all of my signals will be viewed on OSA, the optical spectrum analyzer. And this is the list of the FBGs that I've used, and I've also included FBGT. As you can see here, I've included FBGT inside the pipe. Okay. And then, this is the position. Okay, the principles that FBG use is actually the Bragg wavelength of the FBG gives a shift based on the summation of the two effects, which is strain and temperature. This is strain and this is temperature. So An unstrained FBG where the strain is 0 in above equation provides temperature compensation. So if one of these is 0, we can measure temperature we can produce a temperature compensation system based on this equation. And then this is actually I've derived the equation actually, and by using a classical beam theory for calculating the deflection of beams and a simplified equation of bending of pipe, I've got this. And by including the Bragg wavelength that I've mentioned earlier, we can calculate the strain on each individual FBG strain sensor by using this formula. So it is possible to measure strain by using optical fiber sensors, FBG. Okay, there's not much measurements taken actually. There's actually just 4, which is I took 3 as a main, which is for the comparison between bare and embedded fiber. I would want to compare the sensitivity that the TPU give towards the bare fiber. How does it affect the sensitivity of a bare fiber? How does TPU affect the sensitivity of a bare fiber? That would be interesting to know. So that would be the first measurement that I would want to take. The first one, the comparison between bare and embedded fiber. The second one will be the multi-point measurements, in which I would place 6 FBGs, 3 on each side, just like the previous picture. Okay, and then based on that, I can measure its tensile strain and compressive strain, and for the third one, the temperature characterization as well. Okay, I think you guys might have wonder what this diagram I've shown, because it is more or less similar to the previous one. This is actually the first setup that I've used to capture the sensitivity of the bare FBG and embedded FBG. So actually this is the first step that I've used to capture the bare FBG sensitivity, in which the strain measurement of the FBG is the data is collected by 2.5 cm intervals, and then I've embedded the same bare FBG of the same central wavelength, so we can measure the results. Okay, it is like this. So from here we can from here we can see that the bare fiber and the embedded fiber, the central wavelength shift of the embedded fiber is actually shifting a bit to the right. So this means that the embedded fiber is a lot sensitive than the bare fiber, and this is actually the setup for temperature characterization. This is the bare fiber, and I've embedded the FBG here inside here, just for me to conduct the temperature characterization. Okay, I have to move fast. Okay, this is the data that I've get for bare FBG and embedded FBG in terms of wavelength shift and horizontal displacement. We can see that the embedded FBG's responsivity is actually better than the bare FBG one. It can be proved by the slope of the graph here. And then for multi-point measurements, this is actually the data this is actually the results that I've get, in which the wavelength shift versus horizontal displacement based on each FBGs. So we can see here that FBG1 is actually much more sensitive than FBG3, and FBG3 is more sensitive than FBG5. This is actually due to the position of the FBGs on the setup, just like this one. Okay. And then for the temperature characterization, it is observed that the bare FBG, the embedded FBG, has a much more response, much more steep gradient. So we can say that the response of embedded FBG towards the temperature change is also sensitive as well. And then just to incorporate temperature compensation in the system, I've I have put the FBGT inside the pipe just to see that the system works. And then as I put the FBGT inside the pipe, as I start taking strain measurements, FBGT does not seem to have any response towards strain. This is why I said below here, FBGT is insensitive towards strain variations. So you can see here, FBG3, FBG1, and FBG5 all have wavelength shift. But FBGT, in all horizontal displacements, it will all stay the same. It still stays the same. So from here, we can see that a good temperature conversation system for this strain sensor can be obtained. Okay, and then we look back at our objective, which is those three objectives that I've mentioned earlier, which is the first one, to produce an alternative way in fabricating optical strain sensors. Here at PRC, we have proved that it is possible because we have incorporated the use of 3D printing technology to successfully produce the sensor body, which is, we use the TPU as a sensing pad. As you can see here, this is actually one of the strain sensor that I've fabricated using 3D printer. It is actually very thin, 0.5 millimeter. So it is very conventional to use at any field, at any application that you desire. Okay, and then as for the second one, to improve the sensitivity of optical fiber FBG sensors. So from the graph that we see earlier, that I have shown to you all earlier, it is seen that the wavelength shift, the central peak of the FBG is shifted to the right, in which we call a red shift. So from here, it can be seen that the embedded FBG showed a strain sensitivity of more or less 1.74 times higher than that of the bare FBG, proving that not only that we protect this FBG, but we also make it suitable for in-the-field use. And then, as for the third one, is to produce a reliable and effective strain sensor that can be made ready for any field applications. Here, the obtained results we get is the average wavelength responsivity is 0.0135 nanometers per centimeter of displacement for tensile strain and negative 0.0142 per cm of displacement for compressive strain, which is more or less the same. And both showing a linearity value of up to 99%, proving that this system can be made use in field applications. It would be very useful, and it can be made as a basis for other systems such as extensometer system, because I'm actually developing an extensometer system using this 3D printed sensor. So it's actually ongoing, so I hope that I get the results that I want. Okay.
I think we are
okay. That is all from me. I'm so sorry for taking the time.
Okay.
If you have any question, you can ask.
Interesting talk. So can we take one question from the floor?
Hi. Hello.
Hi.
Hi. Okay. Thank you for your excellent presentation. Right. Very interesting method. 3D printing technology, and you managed to come up with the model, the fiber back grating, and the material is only TPU, right?
Yep. Just TPU.
Just TPU. So let's say from, maybe from other university want to use it. Is it any way that we can collaborate, or you're going to charge us?
That would be very interesting actually, but I have to ask my supervisors to answer that.
Yeah, I'm just wondering because this is quite good. All right, so another question. Okay, so I can see that from your configuration, from your testing configuration, you are using OSA, right? Optical spectrum analyzer. So have you ever thought that maybe this, the output of sensing maybe can be integrated onto some digital platform so that we can integrate it with other, some mobile apps or any software that we can monitor, the output sensing. So have you ever thought on doing this? Because you know, right now is everything is toward, you know, IR 4.0. So we want to like some sort of monitor it over internet, you know, so that the user can just like can monitor it away, you know, remotely. So have you ever thought about this? That's all. Thank you. Thank you.
Thank you for the question. Yes, I have actually thought about that in long term actually, because what I'm trying to develop here is actually a landslide monitoring system using 3D printing technology and fiber break ratings. So in the future, I might need a software that can help me visualize those data in a much more beautiful manner, and then from there we can integrate into mobile apps or apps inside computers and so on. I think it is possible, and a very interesting idea from you.
Yeah, because as you know that normally we need some electrical, I mean, it's a digital data, right? So maybe from this optical data, so maybe we can transform it or convert it into this digital data so that we can monitor it. So thank you so much. Thank you. Congrats.
Thank you.
Okay, thank you very much. Thank you, Ashraf, for his informative presentation. Yeah, I think we can proceed to the next presenter. Ali, this is, I see his last name, Saleh. Is Mr. Saleh here?
Yeah, I will be presenting for this.
Nazrul.
Yeah, Nazrul.
Yeah, please share your screen so that I can see your full name and also I can read your title. Okay, so before I start, may I know which one is you? Are you the second order in the list? Or
the first.
Or the first one. So your name is I assume it's
Hisham.
Muhammad Azrul Hisham Jamaluddin. Okay,
Yeah.
from International Islamic University of Malaysia, and the title of the paper is Investigations of Paper-Based Strain Sensor Using Carbon Conductive Paint. So we have 15 minutes presentation and also followed by 5 minutes Q&A. Yeah, you may start. Thank you.
Okay, can you see my slide clearly?
Yes.
Okay. First of all, I would like to thank the chairperson, Professor Dr. Lim Kok Seng, for giving me this opportunity. And good afternoon, I bet to all of the participants in this conference today. Today, I would like to present regarding my humble work entitled Investigation of Paper-Based Strain Sensor Using Carbon Conductive Paint. My name is Muhammad Azrul Hisham bin Jamaluddin, and I am from International Islamic Institute Malaysia. Basically, there will be 5 parts of my presentation. This is the outline of my presentation. Next, the first part is the introduction part. For the introduction, is the strain sensor can be classified as electronic devices. Then the electronic devices is the device that control electrical energy electrically, which the electron is the fundamental in these electronic devices. Next, there are 2 type of the electronic devices that are currently developed, which are the wearable electronic devices and also the flexible electronic devices. This wearable electronic devices is a handheld electronic device that can be attached to the user's body and is comfortable to wear. It also can be attached to the user's clothes. And this type of wearable devices was developed to monitor the basic physiological parameter such as the movement of the body and also the heart rate of the person. Next, there are plenty application for these devices such as it can be used in a variety of sensor and it also can be used as a movement and health monitoring in human. Next, many researchers have conducted research to produce paper-based devices such as a touch sensor, a gas sensor, and also heating element devices, and including the strain sensor itself. This is because they want to produce a green type of sensor. Next, the strain gauge or the strain sensor is a sensor that can detect the changes of the electrical resistance as it undergoes the deformation in order to measure the strain. For example, if I put the sensor on my finger, then and I bend my finger, then the sensor itself detect the electrical resistance change when the sensor goes. And then there are plenty uses of this strain gauge. For example, it can be used to monitor shape, strain, stress, and also pressure of a system. Next, it can be used also to measure the experimental strength of the material. For example, if we want to measure steel, the sensor onto the steel, and then we measure the strength of the material. Next, it also can be used as a motion monitoring. And the last one, it can be used as a structural health monitoring. Next, there are a few advantages of this paper-based strain gauge. For example, it has high flexibility. The high flexibility means that this sensor can be bent into its maximum limit. Next, this sensor is also easy to fabricate. For example, in my works, I only fabricate the sensor using hand, or I just using a brush and hand to fabricate the sensor itself. Next, the sensor is low in cost, and the sensor is also disposable, which also can mean it's biodegradable. The sensor is can help to reduce the electronic waste in the future itself. Next, the sensor is lightweight since the sensor is produced from paper. Next, the polymer or the polymer that have been used for the sensor is a carbon conductive paint. Next, the polymer is always characterized as insulator. This is because they have extremely low electrical conductivity. However, from time to time, the researchers have developed various electrical conductive polymer by adding the conductive material into the polymer, the mixture of the polymer. Next, the advantage of the conductive polymer over the metal itself is that they are lightweight, easy to process, flexibility, and also some of the polymer is chemical resistant. Then the example of the conductive polymer is the carbon conductive paint itself. And this carbon conductive paint consists of the water, natural resin, conductive carbon, and also the humectant. This is the basic element in the carbon conductive paint. Next, for my research objective is to develop a strain sensor using carbon electrical paint. And the second objective is to investigate the effect of different sensor designs on the sensitivity of the strain gauge. I make a few of design and I test all of these designs to see whether the different design give different sensitivity or not. Next, the third part is the methodology. This is the material that I have been used to produce this type of sensor: carbon conductive paint, the A4 printing paper, usual printing paper, and also a PVC cover. The PVC cover is to mask the shape that I want to produce. This is the design that I've been studying for my work. How I can print this design on the paper. I cut the PVC cover into the design that I want, and then I put the the PVC cover that have been cut into the paper, and then the conductive paint was applied onto the PVC cover, and then the sensor was the paint was let to dry for about 24 hours, and then after the sensor was dry, and then it can the PVC cover can be moved out, and then the sensor was tested using a source meter. This is the experiment setup for my work. The source meter was connected to the computer, and using the software that have been provided by the together with the soft meter. Next is the result and discussion part. For my experiment, I use a current voltage IV graph to find the resistance from my sensor. The voltage was from 0 to 10 volt, and the increment was 0.1 for each increment. And then I take 8 reading for each of the voltage, and I average all of the reading. This is as you can see, this is the result for design 1. In the figure 2 show the result for the design 2, and this is the result for design 3. As we can see, all of these graph show that this sensor obeys the Ohm law, because when the current increase, when the voltage increase, the current also increase. And then, as we can see from figure 3 and figure 2 here, there are slight noise that occur in noise that occur compared to the design 1 sensor. This noise can be occur because of the presence of pinhole on the surface of the sensor. This pinhole will affect the conductivity of the strip itself. Next, this is the result and also resistance of that I find from the graph before. From this table, you can see that design 3 has the highest resistance compared to the other design 3. This may be because of design 3 have more the longest strip compared to the other design, and then most of the folded strip have the highest resistance compared to the usual and bending condition strip. Next, this is the result for the strain for the resistance with strain. This is for the design 1, design 2, and also design 3. From this figure, we can see that the sensor design 1 has the highest sensitivity, which is the 0.667, while the second is the design 3, 0.5, and the last, the design 2 has the lowest sensitivity compared to the other design. Then for the conclusion, the electrical conductive paint changes its electrical properties subject to the mechanical strain. Next, the sensor design number 2 has the lower sensitivity. The carbon electrical conductive paint is a polymer that can be used as a strain sensor element, but the core element in the paint mixture needs to be further characterized to get a better sensitivity. What I mean in this sentence is that I have to study or to develop my own conductive paint or my own mixture of polymer, so that I can get a better result for my sensor. Next, this type of sensor has advantages as it low in cost to be produced. This all from me. Thank you.
So, Nazrul, excellent presentation, very impressive. Okay, the floor is open. Is there any questions for Nazrul? Yeah, perhaps Nazrul can take one question for me while other people,
Yes.
Preparing the next questions. So this material, it seems to have a very interesting elastic electrical property, or you can call it electrical mechanical property. When you stretch it, the resistance will change. And I'm wondering if we can, what happens to the elasticity? So if I apply some strain and then stretch it, and then when I release it, would it go back to the original state? Or
Yes,
it will
yes,
just...
it will.
Yes.
Yeah, from my what I have done before, when I stretch it, I bend the sensor, or the sensor that have been applied with the pen, and when I come back to the original shape, and then the pen also come back to the original shape.
Okay, what happened to the resistance? Did it go back to the same resistance as before?
Yes, go back to the same resistance, because I also wondered before I started my experiment, if I bend the sensor and then I revert to the original shape, whether the resistance come back or not. And then when I test the sensor, the sensor give it back to the original reading, but we have to give it some time. For example, we have to wait for 10 seconds, or at least 15 seconds, and then the reading will come back to the original reading.
I see. It's a very interesting material. Okay, I have another question. How repeatable is this property? Meaning that if I stretch it and I release it, and I stretch it, release it, and repeat 100 times. Although 100 times seems to be a lot, I'm just wondering how many times can we do it before the material begin to disintegrate or begin to lose its property?
Yes. This repeatability is since my experiment is still ongoing, so I will do the repeatability test after this part. So right now I don't know yet how many times do the material will be degrade.
Okay. Thank you. Is there any further questions from the floor? Okay, I guess so. Thank you very much. Thank you, Nazrul, for your interesting presentation. I'm sure our audience learned a lot from you. So I think that will be all for the morning session. So please, we will have a break from now until 2 o'clock, and then we will resume our afternoon session starting from 2 o'clock. And the next chairperson will be Dr. Chong Woo Yi. All right. Oh, okay, I'll see you later. Okay, bye.
Good afternoon. Is the presenter for the 2 o'clock session in?
Thank you, Wee.
Boss,
Thank you for chairing the session.
no problem. Shamil, are you there? Is Mr. Badili in yet? Do you have the presenter from Universiti Technology Petronas with us now? Or the second presenter of the session from Universiti Tun Hussein On, Malaysia? calling for Mr. Badili or Mr. Muhammad from UTP. Mr. Aizat Akmal or Miss?
Hi, hello. My name is Aizat. I'm
Yes.
supposed to be presenting, but I'm currently setting up my camera. Is it okay?
All right. You're from UTP, is it?
Yes.
All right. Okay. Just let me know when you're ready. All right.
Okay, sure.
Okay, very good afternoon to everyone. Welcome back to the final session of the conference. We have three presenters with us today from UTP, UTHM, as well as the last one will be from So without further ado, I'd like to invite the first presenter from UTP, Aizat Akmal, to make his presentation. Aizat, you may take the floor. Aizat, your mic is not all right.
Hello.
Yes, we can hear you now.
I'm sorry. Okay.
Yeah. You need to restart.
Never mind.
All right.
Can do it. Okay. Shall I?
Yes, please.
Okay. Again, my name is Aizat Akmal bin Muhammad Badli. I'm a PhD student from Universiti Teknologi Petronas. My supervisor is Dr. Hisham, the one deliver the keynote speech this morning. Today I would like to present to you a study about validation on laboratory simulated optical fiber sensor, instrumented ball pile imperfection using 3D finite element method. Okay, this presentation will be divided in 5 sections. First, the introduction, and I will share to you some of the literature review, the methodology that I wish for this work, results and discussion, and I will conclude with in the conclusion session. So moving to the introduction, a bit about this work. So basically, this is a ball pile construction. It can be constructed in various ways, and then the design of this pile is using some assumption to meet the loading requirement of the superstructure above it. So this assumption leads to the uncertainty to the design. In confirming this uncertainty, we need to be checked to the real situation or real ground situation in the site. So there is various way. One of it, we use the pilot test, and nowadays due to the advancement and the loading demand capacity by the superstructure, we need to move to instrumented pilot test. The instrumented pilot test can be done using various sensor. The typical one, we use the vibrating wire strain gauge, and with regards to my study, I use the fiber optic sensor. So the fiber optic sensor have a few element, which is the analyzer itself and the cable, as you can see here. So this fiber optic sensor, I using the distributed optical fiber sensor with the method of Brillouin time domain analysis. So when we conduct the instrumented pilot test using this fiber optic sensor, we expected to have a strain profile as shown in this figure. But then after we conducted, this is the reality of the strain profile. As you notice, there is some spike here and there, up and down of the strain profile. Instead, we wanted it to be a nearly perfect inclined line. So this spike, we call it as anomalies, and these anomalies, which actually we expected the pile experiencing some defect, or we call it as imperfection. It can be either necking, bulging, soft to soil intrusion, and whatnot. The typical ball pile imperfection issue or defect issue. So by a study of Badli and Muhammad in 2020, there is an effort to do the ball pile simulation in the laboratory setting to test the typical pile defect, such as necking in the column C, localized necking in the column D. E is the soil contamination, or F is a localized honeycomb condition. So from this study is actually they come to the hypothesis that this ball pile imperfection is able to be studied using the laboratory simulation, whereas the fiber optic able to detect this kind of defect situation. So a bit about this study is actually my study with my supervisor. So this is the loading test arrangement. If you are familiar with the BOTDA analyzer unit, is connected with this instrumented RC column. This RC column is to be built embedded with the fiber optic in the column itself. So I did put some other sensor to validate the LVDT, and then we loaded from the top, and the end is a fix. And this all situation is connected to the BOTD. As you can see, this is some sneak peek of during the loading test. So this is the necking column loaded with the loading arm and connected to the BOTDA analyzer at the back there. So this is some how I would like to share the user interface, how the BOTDA look like during the reading. Okay, so we move forward to the main focus of this study, which is the objective of this work is to validate the hypothesis I said just now, the hypothesis simulated through the laboratory simulation that the DOFSS, the distributed optical fiber sensor instrumentation in bulk pile can detect imperfection of pile in terms of geometrical cross-section and material quality, or we call it as a stiffness. And the validation was performed by back analysis method approach, 2 case studies using real field data of fiber optic instrumented bulk pile conducted by smart sensing technology was used. So technically this work also is a joint venture with smart sensing technologies, right? Is a solely fiber optic contractor in Malaysia. Next, we move to the second section, which is the literature review, a bit one. This is the principle of the Brillouin optical time domain analysis. I bet we are familiar with this situation. So basically, when a light is propagated through an optical fiber, most of the light is passed, and some may travel back, or we call it as back scattered. And the name is Brillouin scattering. So this Brillouin scattering is propagating optical signal interact with an excited acoustic wave and rise the frequency shifted component. The diffracted light just now generated acoustic wave and propagates acoustic velocity, or we call this situation as a Doppler shift. So what is the relation of this Doppler shift to the body of study, such as the bulk pile or the column itself? So the medium density that is temperature and strain dependent, such as the concrete used for the bulk pile and the column, is a medium density that temperature and strain dependent is proportional to the acoustic velocity, or this Doppler shift. So with this relation, we can measure the strain or the temperature of the measured body. This is the study by Kurashima, Horiguchi, and Tateda in 90s. Okay, this is the component of the DOFSS using the Brillouin optical time domain analysis method. We have first the fiber optic cable itself as the sensor. To highlight again, this fiber optic cable is the sensor itself that read the measured body continuously without any. It's different from the point measuring. So we use this strain analyzer, the BOTDA analyzer, which connected to the PC and to read the reaction. Okay, move forward for the numerical simulation part. Is the method of the validation. So we know it as in advanced tools that help in agreeing with the field measure and provide a general recommendation. It confirms the laboratory measurement. So this numerical simulation is a kind of method that can ensure us or give us the confirmation on our actual or assumption or studied before. So there is a 2 method, which is direct and indirect. So we applied the indirect method because it's able to apply to a non-linear back analysis problem without dealing with the complex mathematics, and is an iterative procedure since we need to match the field rate stream profile with the one that we generated from the numerical simulation. There is 2 dimension, it's either 2D or 3D. For this study, of course, we need to employ the 3D due to the suitable to model the asymmetric structure. high accuracy and realistic in-soil structure interaction. Why we need to, why is asymmetric structure? Because when the pile is defected or having an imperfection, so the geometry of the pile is somehow not symmetrical, not a perfect cylinder at all. So the asymmetric structure assumption is better to be considered. So next, this is some past research that have done the numerical simulation on ball pile with embedded fiber optic in it. So by Yuri in 2017, Albuquerque group in 2017 also, and Letizang and Wu in 2015. So for the first group, this first group, they use the hyperpuff, which able to simulate the pile with necking and bulging along the shaft. So it's their study is verified with the thermal integrity profiling. The IP method is another method to know how to know the integrity of the pile itself. Next is in the second group is the RBQQ. They use the LCPC Caesar version 4.07. So they encountered that acceptably estimated the behavior of the pile with some defect. And the last group, they use the NSYS or LS Dyna, and they able to simulate the defect on the pile. So if you are interested, you can read through this literature to gain more detail from their study of numerical simulation. And next, we move to the methodology. The methodology for this work, I use the rock science software. Is a software that meant to analyze the most detailed problem like foundation design, since this is a ball pile design. And then next is able to model the asymmetric model. Some technical parameter to be considered in this using this software, Rock Science 3. So the first one is the soil modeling. We have the recommend and the use value for my study, as you can see in this table. The second one is the number of the iteration tolerance. This iteration tolerance is capping with the converging of the simulation. Next is the external boundary for the surround and the depth of extension, the boundary support, the meshing. Okay, moving forward to the case study. So the case study is about instrumented compression load test on board by using the DOFFS. So, and the second one is using the static load test through maintained load test, and this test is following the standard by ASTM D1143. So some selection criteria is employed to have a better data. First, the site or the case study must be experiencing strain spike, either increase in strain or decrease in strain. Second one is portrait common pile defect. Just to check, can you hear me or you are losing me? Hello?
You're good. And you have 5 more minutes.
Oh, okay. This is the two case study, Mount Kiara site and the Bangi Gateway phase 4 shopping mall. So this is some detail of the Mount Kiara. To highlight, this Mount Kiara site is a mixed development, commercial and residential. The diameter is 900 mm, the length is 32, concrete grade is 45, and the maximum working load is 16,260 kilonewton. So from this side, this is 13 layer of the soil before it reached the hard layer of the sandstone. And the finding from this report, we find that there is a necking, whereas the spike in the strain, and there is a bulging. This bulging is checked to the concrete report. The design is 30 meter cube, but the actual port is it's another way around. The design is 20, but the actual port is 30. So there is a margin of 10 meter cube, at least 1.1 concrete truck extra that been poured in this part. So from this finding, we did expected the model pile to be look like this at the right side. So then next is the second case is Bangi Gateway Phase 4. The diameter is 1.2 meter, length is 31 with the concrete weight of 30, and the maximum working load is 14,400 kilonewton. So for this site, we have 10 layers, and then from the findings, as you can see, there is a high spike at the top, which we expected to have contamination at the top. So as you can see from the British standard, for the concrete grade 30, the design stress is 15,268.10 kilonewton with the strain maximum is 0.001 strain. So as you can see from this strain, for the maximum working load is beyond this limitation. So we did, from the report, they did some concrete coring at the top, first 3 meter. So from this picture, you can see that there is some contamination of the sand or soil at the sample with the concrete, the compression test has lower than the one that we designed. So this is the one that to be modeled in the rock science. So to share to you what is the result in discussion. For the first site, the Montiara site, to repeat, the defect is the necking and bulging. So this is how in the system the modeling is look like. And there is expected necking at the D1, D2. For the D3 is the bulging. So this is the reduction of the cross-section, and this is the increment of the cross-section. So with this situation, after we run the iteration of the simulation, so we get the red line is the field, and the black dotted line is the success iteration. So the interest point is in this section, the necking point, which different between these two lines is 3.3. For this 3%, and the bulging is 0.3 with the volume of 0.24 meter cube. Actually, it's away from the marginal compression just now, due to maybe the concrete is infused into the rock fissures or whatnot. But then, as you notice that the top and the bottom one is not matched properly, this is beyond the study interest, yet it's good to be advanced in the study in future. So next is the second site. To repeat, the defect is a concrete contamination at the top. So we did the variation of the contamination. Actually, we first put as a whole as a one stiffness, but then after some iteration, discovered that the stiffness is different, even though the contamination happening due to various reasons. So as you can see from the red line and the black dotted line, it's nearly matched to each other. And to repeat again, the bottom one is not matched due to the various reasons to be subjected to study in future. And to notice that and highlighted that the concrete stiffness for this two study is actually lesser than the design one, because when we run according to the design concrete grade or concrete stiffness, the matching is not good. But then consider the reality of the concrete pouring situation and whatnot. So we expected to reduce, and yes, we got some good matching of this. All in all, the conclusion for this work is first, the simulating the imperfection bulk file in FEM software resulted same strain profile as measured at the field. As I showed just now, the red and black dotted line is nearly matched to each other. The second one, this conclusion is justified with the data presented within this work without a doubt that the work had validated the hypothesis just now, the one that simulated in laboratory, that this fiber optic sensor instrumentation in BOPA can detect the imperfection of PAL in terms of geometrical cross-section and metric quality, or we call it as stiffness. And last but not least, worth to mention that during the simulation, it's recommended to expect lower concrete stiffness compared to the designated concrete stiffness. All in all, the objectives are achieved. So that's all. I conclude my presentation with thank you, and I open for the next maybe Q&A, right?
Yep. Thank you, Mr. Aizat Akmal. A very interesting study. Any question from the floor? Okay, I have a question. The actual results that you obtained from the two buildings. How do you obtain the results? Do you actually plant the fiber into the pulse?
Yes, we embedded it, cast together with the file.
All right, and that is done by UTP or by a third party company?
The third party, the smart sensing technology.
So that is your collaborator, is it?
Yes.
All right, okay. Any question from the floor? Anyone?
Yes. I would like to have a question.
Seems like it's the norm for this conference that again, everyone is very shy. So in that case, I guess there's no question, and thank you, Mr. Aizat Akmal, for your presentation.
Welcome.
All right, I'd like to invite the second presenter from Universiti Tun Hussein On, Malaysia, Mr. Mahmud.
Can I share my slide?
Yes, sorry. Miss Nick Elena, is it?
Yeah.
All right, okay. You may share your slides. So the second presentation is on the development of a laser source for use as temperature fiber sensors.
Sweet.
All right, we see your slides. You can start whenever you're ready. 20 minutes.
Okay, thank you to the chairperson, and a very good evening to everyone. Today I would like to share my project, which is Modlock based on side polished fiber coated with gold as source for temperature fiber sensor. So without wasting our time, I'm moving on the introduction part, which is fiber laser. Fiber laser usually meant to be a laser with doped fiber as gain medium, or just laser where most of the laser resonator is made of fibers. So the basic structure for the fiber laser, we have the first one is pumping source, resonator, and the gain medium. So there are a few advantages of the fiber laser, which is good reliability and lifetime, high stability, low threshold power, and also narrow line width. And also, fiber laser are important due to the large number of applications such as laser processing, optical fiber communication, optical sensing, and also in medical. Fiber laser also can be set up in a linear cavity, single ring cavity, and also in a figure of 8, and it can be either in active or passive mode lock. And for active mode lock, involve using an external signal to induce a modulations of intracavity light, while passive mode lock do not use external signal to but rely on placing some element into the laser cavity, which causes self-modulations of light. Same with my project, where I'm using the saturable absorber to generate the lock pulses, where the saturable absorber material here that I'm used is a gold. Well, then I have found that a few researchers working on the metal-based SA for pulse fiber lasers, such as carbon platinum, silver nanoparticles, gold nanorods. But the saturable absorber metal composition deposit is in a ratio of less than 10%. Usually in our laser system, silver and gold are used as a pulse compressor, which is metal coated on the fused silica. By taking all the motivations by the previous study, pure gold can be used as an SA and at the same time can act as a pulse compressor. In addition, the gold also has a huge potential application in optoelectronic sensor, solar absorber, and play important roles in optical sensors since it has a good performance and prolonged stability. Well, we all know that nowadays fiber sensor become attracted by all the researchers, including me. And where right now I'm doing the research about fiber sensor. As you all know, fiber sensor use optical fiber for sensing the element. Actually, in fiber sensor, we can measure the temperature, pressure, vibration, and strain. But in my case, I just focusing on the varying of the temperature of the mode-lock fiber sensor. And the method of the measurement, I can see that the changes of the wavelength, output power, and also the SNR value of the mode-lock fiber sensor. So before we move to the sensing part, we have to set up the mode-lock pulse first. And the first part is the preparations of the gold thin film. And the gold thin film was fabricated by using DC magnetron sputtering. Then the DC magnetron sputtering was set at 19.36 of the density with thickness of 10 nanometer. And as you can see, the figure before and after, here is a before, which is a before coated with gold, and after is a what I already coated with gold. And below one, this image of the side polished fiber is using the optical microscope to ensure that the gold is coated on the SPF fiber, on the SPF. After that, the mode-lock pulses result was taken by the OSA and the oscilloscope, and the output spectrum of the mode-lock generate the center wavelength, of 1563.10 nanometer with bandwidth of 11.3 nanometer with output power of negative 13.40 dBm. And for the pulse stream, which was obtained from the oscilloscope, generate repetition rate at 38.5 MHz with pulse interval of 0.0258 microsecond. And the mode-lock pulse wave also obtained from the autocorrelation trace, which is 0.691 picosecond. And for the RF spectrum, we get the repetition rate at 38.5 MHz with SNR value is 44.1 dB. Then the next one, okay. After all the measurement of the mode-lock was taken, I put the SPF, which is coated with gold, into the water, or I immerse it in the water. Where I varying the temperature from the 0 degrees Celsius to 100 degrees Celsius and 100 degrees Celsius to 0 degrees Celsius. I did two process, which is the first one, I heat the water until the 100 degrees Celsius, but during the heating process, I recorded the result as well. Same goes with the cooling process. After I done the heating process until 100 degrees Celsius, I wait for a few minutes and then I go to the cooling process and I have wait to the water have cooling from 100 degrees Celsius to 0 degrees Celsius. To get the temperature which is below the room temperature, I add some ice cube in the water. So the graph shows that the output spectrum that I get when I immerse the SPF Photonics into the water. As you can see here, that when the temperature is increases, the output power decreases, but the resonant wavelength here move towards the longer wavelength. And you can see that in the figure, the blue line which is 0 degrees Celsius of the temperature, we get the wavelength at 1530. Then at 40 degrees Celsius, we get 1542.80 nanometer of wavelength, and at 100 degrees Celsius, we get the longer wavelength compared to the other temperature. Then the next one is the graph for the mod-log fiber sensor of the RF spectrum. And you can see on the left side is the heating process where the temperature from 0 degrees Celsius to 100 degrees Celsius. And for the cooling process, we starting from the 100 degrees Celsius to 0 degrees Celsius. So you can see that the output power here keep decreasing, but the frequency remain constant. Same goes with the cooling process. When I start with 100 degrees Celsius, the output power become negative 50.83, but it keep increasing when the temperature start to decreasing to 0 degrees Celsius. So move to the next slide, which is the data is linearly fitted based on the relationship between resonant wavelength and the temperature. So the relationship between the graph show that the temperature increases. The temperature increases as the wavelength resonance also increases. And also for the cooling process, also the temperature decreases, but the wavelength move towards the longer wavelength. And you can see that the temperature sensitivity of the heating and cooling process is a bit different, which is temperature sensitivity for heating is negative 4079 nanometer per degree Celsius, and for cooling is negative 0.3775 nanometer per degree Celsius, and R squared value is 0.8382, and for cooling R squared value is 0.91224. Then we have a relationship between the output power and SNR value against the temperature, where both process, heating and cooling process, show that as the temperature increases, the output power decreases, but the SNR value keep increases. Same goes with cooling process. This one is I want to prove that when temperature increase, the SNR value keep increasing. As you can see, when I cool the water and I take the temperature from 100 to 0, you can see that SNR value keep decreasing here. So for the conclusion, mod-log fiber sensor coated with gold is successfully demonstrated, and the mod-log fiber sensor show the temperature sensitivity of 0.4079 and 0.3775 for heating and cooling. So we can conclude that as the temperature increases, the laser resonant wavelength move toward the longer wavelength. So and also the SNR value increases as the temperature increases. So
thank you, Ms. Nick Elena.
yeah.
Any question from the floor? Yes, Ms. Nur Fatini.
Okay, hi. I want to ask, can you go back to your design, the KBP design?
Which one?
The set number 7.
Okay.
Yeah, I want to ask, I'm interested with your design, but how you safely immerse your the plate into the water?
Pardon please. How? Sorry.
How do you immerse
the water?
the-
I just put SPF into the water. Immerse it into the water. Means that the whole of the SPF put the water. Not you just drop the water on top of the side of fiber, but you just immerse it all in the water.
Oh, because the fiber is fragile, right? So
yes,
that's not broken.
No, it's not. It's okay. At first I thought it will broken, right? But when I put it in the water, then the lock pass stable. So I just proceed for the temperature sensor by adding but you have to put the side polish fiber on the stable table on the flat surface.
Oh, okay. Next, I want to ask, what is the insertion loss of your fiber? The insertion loss.
Insertion loss of
your side polish fiber.
Insertion loss of the side polish fiber. Oh, do you mean when I splice the fiber?
Yeah.
Actually, when I splice the fiber is 0.00. That's mean that no loss.
0.00.
Yeah. But some of the splice with the maybe the EDF and the isolator 0.01. But overall is below than 0.01, I think, for the loss of the fiber.
Okay, that's all from me. Thank you.
Thank you.
Thank you, Ms. Nur Fatini. Any more questions? Yes, Mr. Muhammad Shamil.
Hello, Alina.
Hi, hello.
So I have this one question. May I look at your setup?
Yes.
Temperature setup.
Temperature setup. Wait.
Because I've been doing the same thing. Yeah. So you see the very temperature, water inside container, 0 degree, right?
Yes,
How do you maintain the 0 degree? Is it?
When I record when I record the result, how I maintain. Actually, when the first one, if starting from the 0 degrees Celsius, I put the ice cube, right? Then I put the thermometer. Then I just check every minute. I check the thermometer. The temperatures of the water. Then after that, I just record the result one by one.
Okay. Okay, thank you. So to be clear, you put ice lah.
Yes, I put ice.
Okay, thank you.
Mr. Aizat Ahmad.
Hi, Mr. Alina. Miss Alina,
Hi.
sorry. Okay, I have one question, but then in two different situations. For your temperature reading or measurement, how did you counter check it with your data? First is either you counter check with the I don't know, maybe your SPF could read the strain also. Maybe you can just calculate it from the strain and then you change to the temperature. Or the second one, you use another sensors to counter check your temperature reading. Yeah, that's all. You got my question?
Yeah, wait. Do you mean that I have to recheck the temperature or?
Yeah, because as I get your study is about to
Temperature
study the
sensor.
temperature, right? So
Yeah.
so there is somehow you measure the temperature of using that sensor. So in regards to that measurement, how do you counter check?
Oh, that in my project I have actually the temperature is I vary the temperature and I look out the result of the mock log pass, right? But to make sure that the result is like I said, that as temperature increases and the output power decreases, that's why I doing the two process, which is the first one is heating process and the second one is cooling process. So I took the two results and then I compare. As you can see that my slide that I did the two process, right, heating and cooling. So the temperature I start from 0 to 100 and I get the result, and 100 to 0. This one is I do the two process is to reconfirm that as the temperature increases, so the output power decreases, and also the SNR value also increases as the temperature increases. That's why I did two process of the temperature.
Oh, okay. I wrongly get you because I thought you are more. I mean, like your sensor is to read the temperature.
Oh, okay. Sorry.
Okay, sorry. Thank you.
Yeah, welcome.
Thank you. We have time for one last question. Can Miss Nick Elena just comment on the repeatability as well as the hysteresis of your sensing experiment?
Yes.
Can you comment on the repeatability? How many times have you repeat your experiment, as well as whether there's hysteresis?
Oh, repeat. I think just twice.
Heating twice, cooling twice.
Both twice for cooling and heating to make sure the result is not really big different.
All right. What about hysteresis? The heating curve and the cooling curve. Are they the same?
Yes, the same. For heating and cooling is the same.
All right. Okay. Thank you, Miss Nick Elena. All right. We come to our last presenter, which is Professor Raymond Uy. His title is Detection of Gravitational Potential of Intense Laser, something very different. Okay. Professor Raymond, are you here?
No, I am the student for the Professor Raymond. I will represent him to present.
I see. Okay. Your name? May I know your name?
Eng Bun.
Okay, Mr. Ng. Okay. You may share your screen and start whenever you're ready.
Okay. Can you all see the screen?
Yes. Please proceed.
Okay, good afternoon, everyone. I'm Eng Bun, PhD student under Professor Raymond. I'm now currently doing the project. This is a theoretical project to measure the gravitational effect from super intense laser by spin squeeze BEC interferometer. Is the outline for my presentation. First, I will give a simple introduction on intense laser and also BEC interferometer. Then I will show the derivation for the gravitational potential generated by the intense laser. And then we will try to design a BEC interferometer to detect this gravitational effect. So here is some previous work that linked to our study. First, the laser beam is a oscillating electromagnetic field. So it has energy and can generate the gravitational field. The study of gravitational field generated by laser start with the Professor Malan Skuli, and recently studied extensively by this Dr. Daniel Larget. Both of them conclude that the gravitational field generated by the laser is still very small to be detected. So in our study, we try to use the BEC interferometer to detect the small variation in the gravitational field. BEC is a ultra-cool atom that have long coherent length and also narrow velocity distribution. So this kind of property can give a high precise measurement. And you can see now the BEC is being suggested to be used as a sensor to detect the oscillating gravitational field. Now the BEC is also used commonly in the BEC interferometer. The gravity effect may induce a small phase change in the BEC. So hopefully the interferometer able to detect this small phase change. Whether it can detect or not is depend on how sensitive this interferometer is. In general, the sensitivity of the interferometer is limited by the standard quantum limit. Delta phase equal to 1 over square root n. The delta phase is the smallest measurable phase change. And this n is the number of atoms in the interferometer. This limit is not the maximum sensitivity. We have another sensitivity called Heisenberg limit, which is more sensitivity than the quantum limit. So now the current study is trying to reduce the sensitivity from quantum limit to Heisenberg limit, which is shown in this field paper. So in our study, we will use the spin squeezing effect in the BEC to reduce from standard quantum limit to Heisenberg limit. This is the current development of intense laser. Now, the most powerful laser is so-called the Eli laser. Eli laser, they use a small amount of energy, but they package the energy into a very small time package. So it's about 200 joule packaged into a few femtoseconds. Then the power can go up to 16 volt, power of 16 volt. And then they focus the laser beam into a few micrometer. The intensity can easily go up to 10 to the power of 23 watt per centimeter. So in the future, they plan to use larger energy, maybe megajoule. Then the intensity can go up to 10 to the power of 27 or 8. So our question is whether when we have this kind of laser, whether we can detect the gravity from the laser. So now we show the derivation of gravitational potential from the intense laser. This is our model. This is our laser beam. Our laser beam is a Gaussian beam, as you see. It's a Gaussian in 3 dimensions. And then the electron electric field and magnetic field is oscillating in the X and Y direction, and the laser pulse is traveling in the Z direction. This is the BEC in the interferometer. We use R1 to represent the coordinate of the BEC, and then the R2 is the laser beam. Using this model and also the equation here, we can compute the gravitational potential. This is so-called the Einstein field equation. We solve this equation to get the H0. H00. The H00 is the small perturbation due to the energy flowing from the laser beam. This U is the energy density of the laser beam. So after we solve for the H00, we can use this equation to get the potential. So this is the final form of the equation for the potential. We solve it using the numerical method to get all these results. This is the parameter we use in the simulation. The radius is about 2 mm. The distance of the radius from the BEC is about 0.4 mm. And the pulse duration is 500 femtosecond. So from this graph, we can see that in the X direction, the potential actually go down almost linearly. So this will give a force in the X direction, and we already compute here. And using the mass of the BEC, we choose it as rubidium. We can compute the acceleration, which is in the order of 10 to the power of -10. So to be able to detect this small acceleration, our BEC sensitivity have to be lower than this value. Here is some of the plot. We vary the radius of the laser beam, and also we vary the pulse duration. So when we have a smaller laser radius, the potential will be smaller. Same for the shorter pulse, the potential also becomes smaller. So we come to a conclusion that to get a larger gravitational force, we need a laser with high energy, with larger radius, and also with longer pulse. So actually, the Eli laser do not fulfill our criteria. And in fact, there is another laser system called NIF laser. The NIF laser, they use a larger energy in the megajoule, and also their pulse duration is in nanosecond. So now we saw how we use the BEC interferometer to detect this small gravitational acceleration. This is the diagram for our interferometer. This is the input. The BEC will come in here, and then this is the beam splitter. It will split the BEC into two. One BEC will go the upper part, and another will go to the lower part. And the yellow region here is where we create the spin squeezing effect. And later I will show the spin squeezing effect can give a higher sensitivity. Our laser is put at here. You can see the distance from the interferometer in the X direction. L1x and L2x is not equal. So this will create a difference in the potential energy experienced by these two parts. Is given as this Ng L2x minus L1x. So this difference in the potential energy will cause the phase shift to be different between the upper part and lower part also. As a result, the output, the number of boson measured at the output will be different also. So now we go back to the spin squeezing part. Use the tripod scheme to create the spin squeezing. In tripod scheme, there will have 3 lasers. These 3 lasers will couple all the internal state together. If the BEC is traveling higher than the recoil velocity of the laser, then this tripod scheme will only affect the internal state. It will not affect the center of mass dynamic of the BEC. So this tripod scheme will create a spin rotation in the BEC. And we can show that the spin rotation will lead to spin squeezing effect in the BEC. This is our equation for spin squeezing. For the spin squeezing effect to occur, this parameter must be smaller than 1. This parameter is proportional to the variance of the spin. The variance of the spin is equal to spin square minus the mean value of spin. Initially, we prepare our BEC in the spin down direction. So the spin vector is at the negative z direction. So in the x and y direction, the spin will be equal to 0. But after we apply the tripod scheme, the spin will be rotated. So now the spin in the x and y direction will have some value. So the variance here will be smaller. And in fact, we saw that the rotation is equal to cosine. This is the rotation angle. So if E is 0, then cosine 0 will give 1. It just means that no spin squeezing. So when we apply the tripod scheme, E will be smaller than 1. And when E is smaller than 1, E can enhance the sensitivity using this equation. As you see, when this spin squeezing parameter is equal to 1, it will reduce back to the standard quantum limit. So when E is smaller than 1, it just means that the sensitivity is already go down the standard quantum limit. So we reduce the quantum phase fluctuation by half with this rotation angle, pi over 3, which is about 60 degrees. By using this equation, together with this equation, we can determine the smallest measurable acceleration. And based on our calculation, the smallest measurable acceleration is in the order of negative 12 meters per second square. So this is much smaller than the gravity we calculated from the gravitational potential. So our conclusion is the sensitivity of the interferometer is able to measure the intent laser. So here's the reference. So I end my presentation here.
Thank you, Mr. Ng. Any question from the floor? Okay, if there's no question, this will be the end of the final session of the conference. Please don't leave yet. So if you all have any question that you would like to ask personally, you all can obtain the contact information of the presenter from the organizer. Okay, and we now will proceed with the closing ceremony of the conference. I'd like to pass the floor to Professor Harif Ahmad.
Thank you so much, Dr. Chong Wei, for your kind assistance in chairing this session. I think it's a very interesting conference that we have from yesterday morning at 10 o'clock until 4 yesterday. Today from 10 to 3, I think it's very fruitful. We have many international speakers and also local, and then we have very interesting student presentation, and the attendance is overwhelming. We have about 73 on the Google Meet, but Google Meet has some limitation, not more than 100, and we have others on the YouTube. I think the response is extremely good, and we are so happy with the present. And also, I must take this opportunity, Dr. Chong. I have to take this opportunity to thank the members of the committee. The members of the committee are actually being undertaken by students. All right, I'm telling you, students are fantastic species. Student is something that you should never underestimate. That they can do fantastic things as long as you give them the right motivation. I would like to sincerely thank to two of our students, Muhammad Ashraf alias and also Muhammad Shamir Muhammad Saad. They are fantastic pair of students, and they help to make the brochures. They help to contact the participants. They do everything, two of them. We only have this idea to have this conference last 2 months because part of the requirement of the Newton funding, we have to share what we have with the public free of charge. The whole idea about research, all the discovery, all the knowledge acquired should be shared to the public, especially to the student. It's not to be locked in some cabinet your idea. We should share the idea. To me, I believe in sharing of idea, and I'm a strong believer of working together. I think when we get this funding, one of the requirement, it must benefit the public. So that's why we have this conference, and we do not charge anything. I know most conference, I think last few months I've been, they charge few hundred ringgit to students. I have to pay some of my students to go some conference. I think our conference is so much better, and we do not charge anybody because it's online. I cannot see the rationale why you have to charge people money, because we don't provide you food, we don't provide you drink, we don't provide you anything except we will share the YouTube and we will have the proceeding, but soft copy that will be done by Ashraf and Shamir, and we will provide the attendance, the certificate of the attendant, and to the speaker and to everybody. So we take this opportunity to thank to them, and not forgetting one of the key member in this organizing committee, Dr. Muhammad Faizal Ismail. Dr. Muhammad Faizal Ismail, he plays a very big role, especially to help to organize this conference. And as I did mention, the two students, and the early days we have Dr. Noor Nashwan, we thank her for that. All right. And then we have the organizing committee like Lin Kok Seng, Dr. Reina, Siti Aisha, Muhammad Khairul, Muhammad Zahid Sami'on, and then Abaya. So we thank you. And I do really hope that you enjoy this conference. We're going to have one more workshop by the year end. That workshop will be face-to-face workshop. If you want to come, you are most welcome, but then you have to pay for your own accommodation. We plan to do at Pulau Langkawi. All right, but there is no registration charge. Only that is your own accommodation, your own transport, and we do not charge. We don't want to make money out of conference. All right. So we believe in giving back the knowledge that we get from our research grant. So I hope that everybody here today enjoy the conference. I hope you have a good time, and I do really appreciate your attendance. Really thanking all the participants today. Have a good day, and do have a good the coming days, a good coming days that you have. Because all this COVID-19, we have to take care of. We have to take care of ourselves. So can I get maybe somebody want to say anything from the attendees? Anybody want to say anything? You are free to put any comment. I hope the conference really is beneficial. Anybody want to say anything? It's an open discussion. Don't be shy. We always like to interact with people. It's online. It's online, so you don't have to be shy. Anybody want to say anything? Want to add in any comment? Okay, I got a lot of the messages here. You are most welcome, Omar. Maybe we get Muhammad Faizal. You want to add in something? Faizal, you want to say something?
Nothing, Prof. I think it's quite okay. Thanks for all the participants, and then I hope you enjoy the conference and can obtain some knowledge, new knowledge from this from the presentations given by the presenters.
Okay, Shami, do not forget to print out the attendance, the certificate of the attendance. Also going to be given to you soft copy. All soft copy online. It doesn't cost us anything. Okay, so thank you for being around. And,
I think Shamil has a request, Prof.
Yeah, Shamil, you want to say something?
Yeah, actually, if we all can, we all open our video. That means your camera, so that we can capture a screenshot of the screen of the conference.
Okay, can we do it now?
Yeah, sure. If possible, everybody can open up the camera just for a while.
Just for a few minutes, we take a screenshot. If you all don't mind.
Take a screenshot, yes.
I see Fauzan here.
Fauzan is here. Very good, Fauzan. Hope you enjoy the talk, Fauzan. Hope Leonard enjoy it. Dr. Chong, thank you. Dr. Rosa, thank you very much. And Dr. Khairul, Anwar, thank you.
Welcome, Prof.
Yeah. Okay, can take a screenshot.
Okay, one.
Everybody inside Shamir, because I think the screen can capture only. We have about 72 now. We have about 69, or maybe about 50.
I think it's randomized on the screen. It's okay. I just screenshot everything I can.
Yeah.
Ambil a few screenshot I put.
Yeah. Yeah.
Dr. Rosa dah posing lah tu.
Okay, one. This is the first screenshot. Okay.
Cepat sikit.
1, 2,
Lengo.
3.
Okay.
Second screenshot.
Okay, bagi peluang kat orang lain.
Asyik buka ni je.
Siapa yang dah screenshot can they give the other people's opportunity. Okay? Okay, Syamil? Sambil dah ambil, kita can leave, so we give the other people the opportunity. So I can leave now, Syamil?
Yes, Prof.
So that we can give them the slot, because the screen only quite limited.
Yeah.
So we give everybody the opportunity, and then kita will share this thing in our PLC punya website for everybody. Alright?
Okay.
So I will leave now. Siapa yang dah ambil gambar can leave, so we can give the slot, the space for the rest. Okay? You may need to take multiple shots. Okay? Alright? Okay, Syamil?
Okay, bro.
Alright, thank you. Bye-bye, Syamil.
Okay, bye. Okay. I'll take a few screenshots lah. Okay, 1. Okay. Save. Okay. Okay, ni last screenshot Okay, try. Okay, 1, 2. Okay. Terima kasih. Thank you for everyone. Thank you for participating.
Thank you everyone for participating. We hope to meet you again soon. Thank you. Thank you very much.